Lesson 1. Introduction to Physical Science and the Scientific Method. We begin our journey at the very beginning, not with a complex mathematical formula or a rigid set of rules, but with a remarkably simple, beautiful way of thinking. In this first lesson, we lay the quiet, steady groundwork for everything else we will learn together. We are going to explore what physical science actually is, and more importantly, we will uncover the elegant, logical tool that humanity uses to understand it. When we look out at the world, at the stars scattered across the night sky, the gentle curve of a falling leaf, or the steady warmth of a morning cup of tea, it can sometimes feel as though the universe is a place of beautiful, random chaos. But beneath that surface, there is a deep, comforting order. There are rules. There is a language that the universe speaks. And as we take this first step together, we are simply learning how to listen to that language. We are preparing our minds to ask the right questions and setting the stage for a journey of gentle discovery. Physical science is, at its heart, the study of the non-living world. You might think of it as the study of the grand stage upon which the play of life occurs. It is the broad umbrella that holds two magnificent, intertwined disciplines, physics and chemistry. Physics is the study of matter and energy, and the fundamental forces that dictate how they dance together through space and time. It is the science of motion, of light, of gravity, and of the invisible waves that carry sound to our ears. Chemistry, on the other hand, is the study of the intimate interactions between different forms of matter. It looks at the tiny, unseen building blocks of the universe and asks how they combine, separate, and transform to create the materials we can touch and feel. To understand both of these vast fields, we rely on a singular, brilliant process known as the scientific method. You might picture this not as a strict, sterile checklist in a laboratory, but rather as a gentle, unfolding mystery, a continuous, thoughtful conversation between us and the universe. This conversation begins with an observation. It starts with the simple, deeply human act of noticing something curious in the world around you and pausing to wonder about it. It is the spark of realizing that the sky turns a brilliant crimson at dusk, or that a heavy stone falls to the earth while a feather drifts. Once we have observed something, our minds naturally move to the next step, which is forming a hypothesis. A hypothesis is simply an educated guess, a thoughtful proposition about why that curious thing happens. It is a quiet whisper to ourselves, suggesting a possible rule or reason that might explain what we have seen. But a guess, no matter how beautiful or logical it sounds, is not enough. This is where the true brilliance of the scientific method reveals itself. We must test our hypothesis through an experiment. An experiment is the physical act of asking the universe a direct question. We set up careful, deliberate conditions to see if our guess holds true when put under the gentle pressure of reality. Finally, after we have watched the experiment unfold, we reach a conclusion. We gather the results, the quiet answers the universe has given us, and we reflect on what we have learned. If our hypothesis was right, we have uncovered a tiny sliver of truth. If it was wrong, we are equally victorious, for we have learned what is not true, and that simply guides us toward a better, more refined question for our next attempt. To truly appreciate the power of this method, we must travel back in time and understand how radical it once was. For many centuries, brilliant minds, most notably the ancient Greek philosophers like Aristotle, relied almost entirely on pure reason and logic to explain the world. They believed that if a thought was deeply logical and beautiful, it must naturally be true. They were armchair thinkers, deducing the laws of nature by thinking about them rather than measuring them. For instance, it was long believed that a heavier object must inherently fall faster than a lighter one, simply because it felt like common sense. But as the centuries turned, during the dawn of the scientific revolution, thinkers like Sir Francis Bacon and the great Galileo Galilei realized a profound truth. They realized that we could not just guess how the universe worked based on human philosophy. We had to step outside, get our hands dirty, and ask the universe directly. Bacon helped formalize the philosophy that observation and experimentation must be the foundation of all knowledge. But it was Galileo who truly brought this idea to life. Imagine him, a quiet, brilliant man, standing on a gentle slope in Italy. Rather than just debating the nature of motion, he took polished bronze spheres and rolled them down carefully constructed wooden ramps. He measured their descent, timing them with the rhythmic dripping of a water clock. Galileo proved that nature does not care what we think is logical. Nature follows its own predictable, mathematically beautiful rules. He showed us that all objects, regardless of their weight, accelerate toward the Earth at the exact same rate when freed from the resistance of the air. The scientific method isn't just a way to memorize facts in a textbook. It is a rebellion against assumption. It is a cycle of boundless curiosity where every answer we find simply opens the door to a deeper, more magnificent question. So you see, this method we are learning is not just an abstract theory reserved for scientists in white coats. It is an incredibly practical, everyday principle that you already use, perhaps without even realizing it. Imagine you walk into your living room on a quiet evening and flip the switch to your favorite reading lamp, but the room remains dark. You have just made an observation. Instantly, your mind forms a hypothesis. Perhaps the bulb has burned out. To test this, you perform a simple experiment by unscrewing the dark bulb and replacing it with a new one. When you flip the switch again and the room floods with warm light, you have reached a conclusion. Your hypothesis was correct. If the lamp had remained dark, your experiment would have proven your initial guess wrong, leading you to a new hypothesis. Perhaps the lamp is unplugged, or perhaps the power to the room is out. The scientific method is the exact same process used by a mechanic diagnosing a sound in your car's engine, or a baker figuring out why a loaf of bread didn't rise, or a gardener tending to a wilting plant. It is simply a structured, peaceful way of learning from our environment, ensuring that our understanding of the world is grounded in reality rather than assumption. We have now grasped how we ask the universe our questions and how we listen patiently for its answers. We have laid a foundation of pure curiosity and careful observation. With this perspective gently settled in our minds, we are perfectly prepared to take our new tools and begin observing the most fundamental behavior of the physical world: movement. Let us hold this understanding here, a complete and satisfying piece of the puzzle. Our next lesson will hand us the adjacent piece, as we embark upon the science of describing the beautiful, continuous motion happening all around us. Lesson 2. Kinematics, the description of motion. In our last session, we laid down the foundational philosophy of how to study the world, learning to observe carefully and ask the universe our gentle questions. Now, we take the next step together and begin to explore the poetry of movement. We are going to immerse ourselves in a branch of physics known as kinematics. The word itself shares a root with cinema, deriving from the ancient Greek word for motion. And just as a cinematic film captures the beautiful, flowing visual of a story without necessarily explaining the mechanics of the camera, kinematics is the science of describing exactly how things move, without worrying quite yet about the invisible pushes and pulls that cause them to move in the first place. It is a discipline of pure observation and description. As you rest there, breathing slowly, you might feel perfectly still, but motion is the fundamental state of the universe. Tonight, we will learn the elegant language required to describe that continuous, wandering dance, setting the stage for all the physical rules we will uncover in the nights to come. Before we can measure how something moves, we must first establish something called a frame of reference. This is a wonderfully grounding concept. Right now, as you lie in your bed, you consider yourself to be at rest. Your walls are stationary, your ceiling is still, and your blankets are resting quietly over you. But if an observer were to look at you from the distant, quiet surface of the moon, they would see you spinning through the dark at over 1,000 miles an hour, carried along by the steady rotation of the Earth. Neither perspective is wrong. Motion is entirely relative. It depends entirely on where you choose to stand and watch. For the sake of our journey tonight, we will choose a quiet, fixed point on the ground as our frame of reference, and from there, we will watch the world move. To describe this motion, we rely on a few incredibly simple, foundational concepts. The first is distance. Distance is a very intuitive idea. It is simply the total length of the path you have traveled. Imagine you are taking a slow, wandering walk through a vast, snow-covered forest. You drift left to examine a frost-covered pine tree, you circle around a frozen pond, and you weave through the quiet, sleeping woods before finally returning to a small cabin. If we were to take a string and lay it down precisely over every footprint you left in the snow, the length of that string would be your distance. It is the full, rich story of your meandering journey. But physics also gives us a second way to measure this, known as displacement. Displacement is entirely uninterested in the wandering path. It is concerned only with two things: where you started and where you finished. If you were to draw a perfectly straight line from the front door of your cabin, through the trees, directly to the spot where you are currently standing in the woods, that straight line is your displacement. It is direct, uncompromising, and highly efficient. If you walk all the way through the woods and eventually return exactly to the front door of your cabin where you began, your distance might be several miles, but your displacement is exactly zero. You are exactly back where you started. Once we understand how much ground we have covered, we introduce the gentle ticking of the clock. This brings us to speed and velocity. Speed is simply a measure of how fast you are covering distance. It is the steady rhythm of miles passing by each hour, or feet passing by each second. It is a single, solitary number. Velocity, however, is a slightly more profound concept. Velocity is speed with a soul. It is speed with a specific direction. If a soft autumn breeze is blowing at 10 miles an hour, that is its speed. But if that breeze is blowing at 10 miles an hour directly toward the east, carrying the morning weather over the hills, that is its velocity. Velocity has intent. This distinction is vital, because moving fast means very little if you do not know exactly where you are heading. Finally, we arrive at the concept of acceleration. In our everyday language, we often use the word acceleration to mean speeding up. We think of a sports car rushing down a highway. But in the quiet, precise language of kinematics, acceleration simply means any change in your velocity. Because velocity includes both your speed and your direction, acceleration happens whenever either of those two things shifts. When a solitary autumn leaf finally detaches from a high branch, it begins its journey at a standstill. As it falls, gravity gently urges it faster and faster toward the earth. This steady increase in speed is acceleration. When a heavy night train approaches a station and the engineer softly applies the brakes, causing the train to lose speed and eventually glide to a silent halt, this decrease in speed is also acceleration. And remarkably, even if you are driving your car at a perfectly steady speed, if you gently turn the steering wheel to round a sweeping curve in the road, you are accelerating. Your speed never changed, but your direction did, and therefore your velocity was altered. Acceleration is simply the mathematics of change. The beautiful, descriptive language of kinematics was largely gifted to us by the brilliant mind of Galileo Galilei in the late 16th and early 17th centuries. Before Galileo, the study of motion was clouded by assumptions. People believed that objects simply moved because it was their inherent nature to seek their natural resting place, and that heavier objects naturally rushed toward the ground much faster than lighter ones. Galileo patiently dismantled these assumptions. He could not rely on modern stopwatches or laser sensors. Instead, he built smooth wooden ramps and carved straight, narrow grooves down their centers. He polished small bronze spheres until they were perfectly round, and he let them roll. To measure the time, he used a water clock, a large vessel that slowly dripped water into a glass at a steady, rhythmic pace. By weighing the water that dripped out while the sphere rolled, he could measure fractions of a second with astonishing accuracy. Through hundreds of quiet, repetitive trials, Galileo noticed a beautiful mathematical rhythm. He realized that the spheres did not just move, they accelerated at a constant, predictable rate. He gave us the ability to chart the future of a moving object using simple arithmetic. He showed humanity that the universe is not random, but is instead governed by a continuous, unbroken logic that we could translate into the language of mathematics. This unbroken logic is not merely a historical footnote. It is the invisible architecture that supports so much of our modern world. When you use an application on your phone to navigate a long road trip, the satellite system is performing the exact same kinematics calculations that Galileo pioneered. By constantly measuring your changing displacement against the steady march of time, it calculates your velocity, accounts for the slower speeds of traffic, and gently predicts exactly what time you will arrive at your destination. It takes the complex, winding journey of your life and translates it into a comforting, predictable certainty. We have now mapped out the descriptive language of space and time. We understand distance and displacement, speed and velocity, and the steady changes of acceleration. We know exactly how things move through the world. But motion does not simply happen on its own. A leaf does not fall without a tug, and a rolling sphere does not stop without a push. There are invisible hands at work all around us. Take a deep, slow breath. Let the mathematics of motion settle peacefully in your mind, and prepare to close this chapter. When we return, we will uncover the forces behind the motion, diving deeply into the profound and beautiful laws of dynamics. Lesson 1. Introduction. Lesson 3. Dynamics. Newton's laws of motion. In our last session, we learned to describe the beautiful, wandering paths of moving objects. We learned the gentle mathematics of kinematics, observing distance, velocity, and acceleration without asking where they came from. Now, we are ready to ask the deeper question. We are ready to look behind the curtain of motion and discover the why. Welcome to dynamics. In this lesson, we will uncover the invisible, silent rules that govern every push, every pull, and the beautiful, underlying stubbornness of all objects in our universe. When you watch a leaf tumble across the grass, or feel the gentle resistance of a heavy door as you push it open, you are experiencing dynamics. You are interacting with the very fabric of physical reality. Tonight, we will explore the 3 elegant laws that perfectly describe this interaction. We will take our time, allowing the profound simplicity of these rules to wash over us, and we will discover how a quiet intellect in the 17th century managed to explain both the falling of an apple and the slow, eternal orbiting of the moon. The entire foundation of dynamics is built upon a single, simple idea, the concept of a force. In the language of physics, a force is nothing more complicated than a push or a pull. It is an influence that tries to change the way something is moving. When you press your head softly into your pillow, you are applying a gentle downward force. When the pillow presses back up against you, supporting your head in the dark, it is applying an upward force. Sir Isaac Newton captured the behavior of these invisible pushes and pulls in 3 magnificent laws of motion. Let us begin with the first law, which is often called the law of inertia. Inertia is a beautiful, comforting concept. It describes the natural, quiet stubbornness of all matter. The first law states that an object that is peacefully at rest will remain exactly at rest, and an object that is in motion will stay in motion, traveling in a perfectly straight line at a constant speed, forever unless an outside force gently or sharply interrupts it. Matter, quite simply, likes to keep doing exactly what it is already doing. You might wonder then why a heavy book sliding across a long, smooth wooden table eventually slows down and glides to a halt. It seems to violate this law, as if it naturally wants to rest. But Newton realized that the book is not stopping on its own, it is being interrupted. As it slides, the microscopic bumps and ridges of the book's cover are softly scraping against the microscopic ridges of the table. This creates an invisible, opposing force called friction. The book wants to slide forever, honoring its inertia, but the friction reaches out and gently pushes against it, stealing its momentum until it is still. If we could somehow remove all friction and take that book into the deep, empty vacuum of space, a single gentle push would send it drifting in a straight line for all eternity. Now we move to the second law of motion. If the first law tells us what happens when forces are perfectly balanced, the second law tells us exactly what happens when they are not. It connects three fundamental concepts: force, mass, and acceleration. Mass is simply the measure of an object's inertia, or how much stuff is packed inside it. A heavier object has more mass, and therefore more stubbornness. Imagine standing in a quiet, moonlit garden. Before you are two wheelbarrows. One is entirely empty, and the other is filled to the brim with heavy, solid river stones. If you step up to the empty wheelbarrow and give it a firm push, applying a force, it will eagerly leap forward, accelerating quickly. But if you apply that exact same push to the wheelbarrow full of stones, it will barely creep forward. Its massive inertia resists your force. The second law tells us this in a beautiful mathematical whisper. To achieve the same graceful acceleration, a larger mass requires a much larger force. It is the universe's way of ensuring that heavy things require great effort to move, grounding our physical world in predictability and substance. Finally, we arrive at the third law of motion. This law speaks to the absolute symmetry and balance of the universe. It tells us that forces never, ever exist in isolation. They are always born in pairs. The third law states that for every single action, there is an equal and opposite reaction. This means you cannot touch the universe without the universe touching you back with the exact same intensity. If you press your hand firmly against a cold brick wall, you might think you are the only one doing the pushing. But physics tells us that the wall is pushing back against your hand with the exact same amount of force. If the wall were not pushing back, your hand would simply pass through it. This law reveals a deeply connected, collaborative universe. Every interaction is mutual. When a bird flies through the morning sky, its wings push the air downward, and in perfect, obedient response, the air pushes the bird upward, holding it aloft. To truly appreciate these three laws, we must briefly visit the world of a young Isaac Newton in the year 1665. A great plague was sweeping through England, forcing Cambridge University to close its doors. Newton, seeking safety, retreated to his quiet family farm at Woolsthorpe Manor. There, in the absolute stillness of the countryside, with no professors or deadlines to distract him, his mind was free to wander. Legend tells us he was sitting in his garden when he watched an apple fall from a tree to the grass below. While others saw a mundane occurrence, Newton saw a profound mystery. He realized that the apple didn't just fall, it was pulled by an invisible force radiating from the earth. But his true genius lay in looking past the apple, up into the sky, toward the pale moon. Before this quiet moment in the garden, humanity believed that the heavens and the earth operated under completely different sets of rules. The heavens were thought to be perfect, divine, and ethereal, while the earth was heavy, flawed, and mechanical. Newton shattered this division. He realized that the very same invisible force pulling the apple to the ground was also reaching out across the vast emptiness of space, gently tugging on the moon, keeping it tethered in its eternal orbit. When he finally published these ideas in 1687 in his masterpiece, the Principia, he unified the cosmos. He proved that whether it is a falling leaf, a sliding book, or a distant planet, the entire universe dances to a single, harmonious set of physical rules. These magnificent laws are not just ink in an ancient book. They are the rhythmic heartbeat of your everyday life. When you are sitting quietly in a small wooden boat on a still, glass-like lake, you take an oar and push the heavy water backward. Because of the first law, your boat wants to stay at rest. Because of the second law, the heavy mass of the boat requires a firm push to get it moving. But it is the beautiful third law that actually grants you passage. You push the water backward into the wake, and in perfect symmetry, the water pushes your oar and you, and the boat softly forward into the mist. Every step you take on a sidewalk is a testament to this truth. You push backward against the turning earth, and the earth, massive and steady, pushes you gently forward toward your destination. We now understand the invisible pushes and pulls that cause all motion, and the stubborn, beautiful mass that resists them. We can see the interconnectedness of every action and reaction. But forces and motion require a kind of currency to operate an underlying spark that makes all this physical action possible in the first place. You cannot push a wheelbarrow or row a boat without expending something from within yourself. Let us rest our minds here for a moment, letting Newton's profound universe settle around us. When we return, we will begin our study of this cosmic currency, diving into the warm, vital concepts of work, energy, and power. Lesson 1. Introduction. Lesson 4. Work, energy, and power. In our last session, we sat quietly with Sir Isaac Newton and discovered the invisible pushes and pulls that dictate the movement of everything in our universe. We learned about forces, mass, and the beautiful symmetry of actions and reactions. But to exert a force to actually make something move against its own stubborn inertia requires something more. It requires a profound underlying spark. In this lesson, we will explore the concepts of work, energy, and power. You can think of this as the fundamental accounting system of the physical universe, a perfect, unbroken ledger that ensures everything remains perfectly in balance. Whenever anything happens, from the soft beating of your heart to the distant explosion of a collapsing star, this cosmic currency is being exchanged. As we drift into this topic, simply let the gentle rhythm of these energy exchanges wash over you. In our everyday language, we use the word work to describe a wide variety of tiring activities. Sitting at a desk, reading a difficult book, thinking deeply about a complex problem, or standing in one place holding a heavy box, all feel very much like work. But in the quiet, precise language of physics, work has a very specific and beautiful definition. Work is done only when a force successfully moves an object over a distance. Imagine you are standing before a massive, solid stone wall. You place your hands flat against the rough stone and push with all your might. You push until your muscles ache, and you are entirely out of breath. You have certainly spent a great deal of effort, but physics gently tells us that because the wall did not move, you have done exactly zero work. Work is not about the struggle, it is about the tangible result. To do work, your force must cause a displacement. If you pick up a small pebble from the ground and place it delicately on top of a low wall, you have done actual physical work, because you applied an upward force against the pull of gravity, and the pebble traveled a distance. But where does the ability to do this work come from? This brings us to energy. Energy is, quite simply, the capacity to do work. If work is the act of moving something, energy is the stored potential to make that movement happen. It is the currency you must spend to alter the universe around you. Energy reveals itself in two primary forms, and they are in a constant, graceful dance with one another. The first is kinetic energy. The word kinetic comes from the ancient Greek word for motion. This is the energy of anything that is currently moving. A rolling bowling ball, a soaring eagle, and a softly tumbling stream all possess kinetic energy. The heavier the object is, and the faster it moves, the more kinetic energy it carries. The second form is potential energy. This is the energy of quiet anticipation. It is stored energy, waiting patiently to be released. Imagine a classic archer standing in a quiet, sunlit forest. When she pulls back the string of her bow, she is doing work, pulling the string over a distance. But where does that effort go? It is quietly stored in the bent wood and the taut string as elastic potential energy. The bow is perfectly still, yet it holds a deep, quiet promise of motion. The moment she relaxes her fingers, that stored potential energy instantly and beautifully transforms into the kinetic energy of the flying arrow. Another kind of potential energy is gravitational. When you lift a heavy book and place it on a high shelf, you have done work against the Earth's gravity. That work is not lost. It is stored in the book simply because of its new height. It rests there on the shelf, holding onto its gravitational potential energy. If the book were to gently slip over the edge, that stored energy would immediately convert into kinetic energy as it fell back toward the floor. Now that we understand work and energy, we must introduce the steady ticking of the clock. This brings us to power. Power is not about how much work you do, it is about how fast you do it. Power is the rate at which work is performed, or the rate at which energy is transferred. Imagine a flight of wooden stairs leading up to a cozy bedroom. If you slowly and quietly walk up those stairs, taking your time, you are doing a specific amount of work, lifting the mass of your body against gravity to a new height. Now, imagine you run up those exact same stairs as fast as you can. In both scenarios, the total amount of work done is completely identical. You move the exact same weight, the exact same distance. But when you run, you are doing that work in a much shorter amount of time. Therefore, running up the stairs requires much more power. Power is simply the intensity of the work being done. To truly appreciate these concepts, we must recognize one of the most comforting and foundational truths of our universe, the law of conservation of energy. Discovered and proven through the tireless work of brilliant scientists in the 19th century, this law states a profound reality. Energy cannot be created from nothing, and it can never be destroyed into nothingness. The total amount of energy in the universe was set at the very beginning, and it has remained exactly the same ever since. Energy can only gracefully change its form. Consider a heavy brass pendulum swinging back and forth in a tall grandfather clock. When the pendulum reaches the very top of its gentle arc, for a microscopic fraction of a second, it pauses. It stops completely. At this exact moment, it has zero kinetic energy, but it has maximum gravitational potential energy because it is at its highest point. As it begins to fall back down, it loses its height, but gains speed. The potential energy is smoothly poured into kinetic energy. At the very bottom of its swing, it is moving its fastest. Here, its potential energy is depleted, but its kinetic energy is at its absolute maximum. It swings back and forth, endlessly trading potential for kinetic and kinetic for potential, in a perfect, closed loop of conservation. A dedicated physicist named James Prescott Joule helped prove this conservation by showing that even mechanical energy that seems to disappear is actually just changing form. He built a clever device where falling weights turned a paddle wheel inside a sealed barrel of water. As the weights fell, they did mechanical work, spinning the paddles. He found that this work did not just vanish into the void, it stirred the water, and in doing so, it softly raised the water's temperature. He proved that mechanical energy could be smoothly transformed into thermal energy, bringing the study of physics and heat together forever. So you see, when we talk about a powerful car engine, or when we check the wattage of a quiet bedside lamp in our home, We are witnessing these exact physical principles in action. An engine is not creating energy out of thin air. It is simply a machine designed to take the chemical potential energy stored quietly in its fuel and rapidly convert it into the kinetic energy that moves the heavy metal down the highway. The speed at which it can perform this conversion determines its horsepower, a charming unit of power coined by James Watt to compare his steam engines to the strong draft horses they were replacing. Even your own body is a masterpiece of energy conversion, taking the chemical energy of the food you eat and seamlessly turning it into the kinetic work of your beating heart and expanding lungs as you rest. We have just seen how energy flows and changes form to accomplish work, and how no energy is ever truly lost. But as James Prescott Joule discovered with his swirling barrel of water, one of those forms, heat, has a magnificent, complex life of its own. It is the form of energy that most often slips away from our machines, warming the air around them. Let us drift seamlessly away from the solid mechanics of pushes and pulls and move into our next topic, where things begin to warm up. Let your mind relax as we prepare to explore the comforting laws of thermodynamics and heat transfer. Lesson 1. Introduction. Lesson 5. Thermodynamics and heat transfer. Welcome back. Allow yourself to sink just a little deeper into the quiet comfort of where you are resting. Take a slow, deep breath and let the tension gently leave your shoulders. In our last session, we explored the grand, unbroken accounting system of the universe, tracing the flow of work, energy, and power. We learned the comforting truth that energy is never truly lost to the void. It simply changes its shape, transitioning gracefully from one form to another. Tonight, we will focus our minds on one of energy's most familiar, reassuring, and essential forms. In this lesson, we will explore thermodynamics, the study of heat and temperature, and the gentle, unbreakable laws that dictate how warmth spreads through the world. To begin our understanding, we must softly untangle two words that we often use interchangeably in our daily lives: temperature and heat. To the physicist, they are deeply related, but wonderfully distinct from one another. Let us start with temperature. To truly visualize temperature, we must shrink our perspective down to the impossibly small, unseen world of atoms and molecules. Even when an object looks perfectly still, like the heavy, solid wood of a bedside table or the cold iron of a winter fence, its atoms are not entirely at rest. They are shivering. They are vibrating in place, performing a microscopic, continuous, and silent dance. Temperature is simply a measurement of how vigorously those tiny particles are moving. It is a way to gauge the average kinetic energy within a specific object. When the atoms are moving slowly, vibrating with a gentle, lazy rhythm, we perceive that object as cold. But when we add energy to the object, those particles begin to wiggle and bounce against one another with tremendous enthusiasm. As their invisible dance becomes faster and more frantic, the temperature of the object rises, and it feels warm to our touch. Heat, on the other hand, is the actual movement of that energy. If temperature is a condition, heat is an action. Heat is the flow of thermal energy from an object with a higher temperature to an object with a lower temperature. Heat is the great, patient equalizer of the physical world. It is the universe's natural attempt to share energy until everything is perfectly, peacefully balanced. This sharing of warmth happens in three distinct, beautiful ways. The first method is called conduction. Conduction is the transfer of heat through direct physical contact. Imagine coming inside on a crisp, freezing winter evening and wrapping your cold hands around a freshly poured, steaming mug of tea. Instantly, you feel a deep, soothing warmth seep into your skin. What is happening on a microscopic level is a cascade of tiny collisions. The fast-moving, highly energetic atoms of the hot ceramic mug are softly bumping into the much slower-moving atoms of your skin. With every tiny collision, a fraction of energy is passed along, causing the atoms in your hands to vibrate faster, gently warming you up. Conduction relies entirely on closeness. It requires atoms to physically touch and share their momentum. The second method of heat transfer is convection. While conduction happens best in solid objects, convection is the way heat travels through fluids, which, in the language of physics, means both liquids and flowing gases. Convection is a story of currents and buoyancy. Think of a pot of water placed over a low, steady flame. The water at the very bottom of the pot, resting directly above the fire, warms up first. As it warms, its molecules move faster and push slightly further apart from one another. This makes that bottom layer of water lighter or less dense than the cold, heavy water above it. Because it is lighter, this warm water gently rises to the surface. As it moves away from the flame, it eventually cools, becomes heavier, and slowly sinks back down to the bottom to be warmed once again. This continuous, rolling cycle of rising warmth and sinking cold creates a convection current. It is exactly the same gentle mechanism that creates the invisible winds in our atmosphere, circulating the sun's warmth across vast oceans and sweeping continents. The third and final way heat travels is through radiation. Both conduction and convection require matter. They need physical atoms to bump or flow. But what happens when there is no matter at all? How does the immense warmth of the sun reach the Earth, crossing 93 million miles of cold, empty, silent vacuum? The answer is thermal radiation. Heat can travel as an electromagnetic wave, an invisible ripple of pure energy. When you sit in front of a glowing campfire and feel your face grow warm, you are not just feeling the hot air blowing toward you. You are actually absorbing invisible waves of infrared light radiating outward from the glowing embers. Radiation is warmth unbound by physical matter, flying free across the dark expanse of space. These gentle, invisible transfers of warmth are strictly governed by the laws of thermodynamics. There are 4 laws in total, but it is the second law that reveals the most profound and poetic truth about the passage of time. The second law of thermodynamics states that heat will always, naturally, flow from a hot object to a cold object, and never the reverse, unless you force it to do so by actively doing work. If you place a hot cup of coffee on a desk in a cool room and simply leave it alone, it will inevitably cool down, generously sharing its heat with the air in the room until both the coffee and the room are the exact same temperature. The room will never spontaneously gather its ambient heat and force it back into the coffee cup to warm it up. This one-way street of heat flow introduces us to the concept of entropy. Entropy is often described in textbooks as the measure of disorder or randomness in a system. The universe, according to the second law, is constantly moving toward a state of higher entropy. But you do not need to think of disorder as chaos or destruction. Instead, think of it as a natural, relaxing, spreading out of energy. Imagine a single drop of dark blue ink falling gently into a still glass of perfectly clear water. At first, the ink is highly organized, a concentrated little sphere of deep, intense color. But slowly, without you ever stirring it, the ink begins to drift and spread. The color diffuses outward, growing lighter and lighter until the entire glass is a uniform, pale blue. The ink will never spontaneously gather itself back together into a single, concentrated drop. The universe is much like that quiet glass of water. Its concentrated pockets of intense heat and energy, like blazing, burning stars, are slowly, patiently radiating their warmth out into the cold void. Entropy is simply the universe winding down, relaxing into a smooth, quiet, and even state of perfect thermal equilibrium. It is a slow, cosmic exhale. We can, however, temporarily fight this natural flow of entropy in our daily lives, but it requires continuous effort. Consider the refrigerator humming quietly in your kitchen. It might seem like a machine designed to create coldness, but physics tells us that cold is not a tangible substance. Cold is merely the absence of heat. Your refrigerator works by using an electric motor and a special chemical refrigerant to actively absorb the ambient heat from the food inside the insulated box, and then pump that heat outward, releasing it through the warm coils on the back of the appliance. It must constantly perform mechanical work to push heat in the unnatural direction from the cool interior to the warmer kitchen. The very moment you unplug it, the second law of thermodynamics takes over, and the warmth from the room immediately begins to seep back inside, seeking that peaceful equilibrium. As we have just seen, thermal energy does not just bump and flow, it can also radiate outward in invisible, undulating waves, crossing vast, empty distances to deliver its warmth. This beautiful realization brings us perfectly to our next natural step. Having understood the waves of heat, let us turn our minds to the fascinating nature of waves themselves. Rest here for a moment, in the comfortable, balanced equilibrium we have found, as we prepare to explore the rhythmic mechanics of the physical world and the gentle sounds they carry to our listening ears. Lesson 1. Introduction. Lesson 6. Wave Mechanics and Sound. Welcome back. Take a moment to settle deeply into your space, allowing your breathing to match the slow, steady, and peaceful rhythm of the concepts we are exploring together. In our last session, we watched how thermal energy naturally flows and spreads, sometimes radiating outward in invisible, undulating waves. Now, let us take that beautiful image and explore it fully. In this lesson, we will dive into wave mechanics. We are going to discover exactly how energy can travel across vast, open distances without permanently moving the matter it travels through. It is a brilliant, cooperative trick of nature, a gentle relay race of atoms that ultimately brings us the magnificent gift of sound. As you rest and listen to the tone of my voice, you are already participating in the very physics we are about to uncover. To understand a wave, we must first change how we think about movement. Usually, when we think of something moving from one place to another, like a thrown baseball or a falling leaf, we are watching a physical object change its location. But a wave is entirely different. A wave is simply a disturbance, a pulse of pure energy that travels through a medium, while the medium itself largely stays exactly where it is. Imagine you are standing at the edge of a perfectly still, glass-like pond. If you toss a small pebble into the center, you will immediately see a perfect ring of ripples expanding outward toward the shore. It looks as though the water itself is rushing outward, but if you watch a single fallen leaf resting on the surface of the pond, you will notice something magical. As the ripple passes beneath it, the leaf does not move forward with the wave. It simply bobs gently up and then gently down, returning to its original resting place. The water did not travel to the shore, only the energy of the dropped pebble did. The water was merely the temporary vehicle for that energy. To describe this traveling energy, we use a few simple visual terms. If you picture a wave as a smooth, rolling hill, the absolute highest point of that hill is called the crest. The lowest point, the deep valley between the rolling hills, is called the trough. The distance from the top of one crest to the very top of the next crest is known as the wavelength. And finally, we have frequency, which is simply a measure of time. Frequency tells us how many of those crests pass by a single, fixed point in 1 second. But the sound of my voice reaching your ears right now does not move like those rolling ocean waves. Ocean waves move up and down, which physicists call transverse waves. Sound, however, is a special kind of wave called a longitudinal wave. Instead of moving up and down, sound waves push and pull in straight lines. Think of a long metal spring toy or a musical accordion. If you stretch the spring out and give one end a sharp push forward, you will see a cluster of coiled metal bunch tightly together and travel all the way down the line. In the air around us, this is exactly what sound is doing. When I speak, my vocal cords vibrate. They physically push against the air molecules in my throat. Those molecules bump into their neighbors, bunching up in a moment of high pressure called compression. Then they bounce back, spreading apart into a moment of low pressure called rarefaction. This rhythm of pushing and pulling, bunching and spreading travels outward at over 700 miles an hour, an invisible domino effect in the air, until that final air molecule softly taps against your delicate eardrum, passing the energy into your mind. Because sound relies entirely on this physical domino effect, it comes with a profound limitation. It absolutely requires a medium to travel through. It needs a substance, whether it is a gas like the air, a liquid like the ocean, or a solid piece of wood or steel. The molecules must be there to bump into one another. This leads us to a beautifully eerie truth about our universe. The vast expanse of outer space is a vacuum, meaning it is entirely empty of matter. There is no air, no gas, no substance to compress and expand. Therefore, space is a place of absolute, unbroken silence. Even if two massive stars were to collide in the most violent explosion imaginable, if you were floating nearby in a spacesuit, you would not hear a single whisper of it. The visual flash would be blinding, but without a medium to carry the mechanical wave, the energy of sound simply cannot exist. When sound does have a medium, the nature of that medium dictates how the sound behaves. We are used to hearing sound travel through the air, but air is actually a rather slow and inefficient medium because its molecules are floating far apart. If you were to dip your head underwater, you would find that sound travels more than 4 times faster. This is because liquid water molecules are packed much closer together, allowing them to pass the vibrating energy along much more quickly. And in a solid, like a long steel train track, the atoms are locked tightly, arm in arm. This is why, long ago, people could press their ear against a steel rail and hear the metallic vibration of an approaching train miles before the sound ever reached them through the air. The shape of the wave also determines exactly what we hear. We measure the frequency of sound in a unit called hertz. A slow, wide wave with a long wavelength creates a low, calming pitch like the deep, distant rumble of thunder or the lowest key on a grand piano. A rapid, tight wave where the crests are packed closely together creates a high, singing pitch like the chirp of a small cricket or the chime of a tiny silver bell. Furthermore, the height or amplitude of the wave dictates its volume. A tall, energetic wave is loud, while a short, gentle wave is a quiet whisper. This mechanical behavior of sound is not just for our listening pleasure. It is a vital tool for navigation and survival in the natural world. Animals like bats and dolphins live in environments where light is often useless, the pitch-black night sky or the murky depths of the ocean. To survive, they use a biological sonar called echolocation. They produce a sharp, high-frequency click, and then they wait in perfect silence. When that sound wave strikes an object, like a small moth or a hidden fish, the wave bounces backward, returning as a faint echo. By feeling the precise timing and direction of that returning wave, these animals can map their dark surroundings with astonishing, crystal-clear accuracy, using echoes as their eyes. We have adapted this exact same physics to build sonar systems for submarines and even ultrasound machines in hospitals, using the gentle echoes of high-frequency sound to safely look inside the human body. We have spent this time appreciating how the physical bumping of atoms can carry energy across a room or across an ocean. But as we established, these waves of sound are forever bound to the physical matter of the world. They are trapped on Earth, unable to cross the silent, empty void of space. Yet, when we look up at the night sky, we see the light of distant stars. There is another kind of wave, a kind of energy that requires no air, no water, and no physical dominoes to fall. It is a wave that can cross the deepest, emptiest stretches of the cosmos. Let us rest here for a moment in the quiet. When we return, we will prepare our minds to explore the dazzling and mysterious mechanics of electromagnetism and light. Lesson 1. Introduction. Lesson 7. Electromagnetism and Electric Circuits. Welcome back. As you lie there in the quiet, allow the physical world around you to fade just a little more into the background. Let your breathing settle into a slow, comfortable rhythm. In our previous sessions, we have traced the paths of moving objects, felt the warm flow of thermal energy, and listened to the mechanical, rhythmic waves of sound. Now, we are going to take a step deeper into the invisible architecture of the universe. We are going to explore a force that, for much of human history, seemed entirely like magic. In this lesson, we will immerse ourselves in the study of electromagnetism and electric circuits. We will learn how tiny, silent charges bring light to our darkest nights, power the modern world, and invisibly bind the fabric of physical reality together. Rest easy and let us unravel this beautiful mystery. To understand electricity, we must first look to the incredibly small. Although we will explore the atom more deeply in a future lesson, for now, we simply need to know that all matter is filled with tiny, virtually weightless particles called electrons. These electrons carry a fundamental property known as a negative electric charge. In the quiet rules of physics, opposites attract and likes repel. Two negative charges will gently push away from one another, while a negative and a positive charge will reach out and pull each other close. In certain materials, like a long, thin thread of copper wire, these negative electrons are not held very tightly by their atoms. They are free to wander. When we encourage these free electrons to all move together in the exact same direction, we create electricity. Specifically, we create an electric current. You can visualize an electric current exactly as you would visualize a broad, slow-moving river. The water itself represents the electrons. Current is simply the measure of how much water is steadily flowing past you at any given moment. But a river does not flow unless there is a reason usually. A gentle slope causing gravity to pull the water downward. In an electrical wire, that slope, that silent pressure pushing the electrons forward, is called voltage. Voltage is the electrical push. It is the deep, quiet potential energy that desires to move the charges from one place to another. A common battery, resting quietly in your hand, is essentially a pump waiting to provide that voltage. It has a high pressure of electrons trapped at its negative end, and an empty, welcoming space at its positive end. However, as the river of electrons flows, it does not do so without challenge. The copper wire is filled with other atoms, and as the electrons move, they softly bump and weave through this atomic obstacle course. This natural slowing down of the current is called resistance. Think of resistance as a series of smooth, heavy stones resting in the bed of our river. They do not stop the water, but they do slow its progress, causing the water to gently churn. In a wire, this churning friction creates heat. It is this very resistance that warms the coils of a toaster, or causes the thin filament of an old-fashioned light bulb to glow with a bright, welcoming light. For this magnificent system to work, however, it requires a circuit. A circuit is a continuous, unbroken loop. The electrons must have a clear path to leave the voltage source, travel through the wire, perform their work against the resistance, and return home to the other side of the battery. If you imagine cutting a deep trench for a river, but putting a solid dam right in the middle, the water stops flowing instantly. This is exactly what happens when you flick a light switch off. You are simply lifting a tiny metal bridge, breaking the loop, and the silent river of electricity immediately comes to a peaceful halt. For many years, the steady flow of electricity in a circuit and the magnetic pull of a compass needle were thought to be two completely separate, unrelated phenomena in nature. But in the year 1820, a Danish physicist named Hans Christian Ørsted was giving a quiet lecture to his students. He had a simple electric circuit on his wooden table, and entirely by chance, a magnetic compass was resting nearby. When Ørsted connected the wire and allowed the current to flow, he noticed something profound. The needle of the compass gently twitched and turned away from the north. In that single quiet moment of observation, the universe revealed a grand secret. Electricity and magnetism are not separate. They are two sides of the exact same coin. Whenever electrons move, they effortlessly weave an invisible, spiraling magnetic field around the wire. By taking a long piece of wire and carefully wrapping it into a tight coil, we can concentrate that field. If we run a current through that coil, it becomes a powerful electromagnet, a magnet that we can control, turning its invisible pull on and off with the simple flick of a switch. But the true magic, the discovery that built the modern world, came a few years later through the intuitive genius of an English scientist named Michael Faraday. Faraday was a self-taught man who lacked formal mathematical training, but he possessed a brilliant, visual imagination. He wondered, if moving electricity could create a magnetic field, could the reverse also be true? Could a magnetic field create electricity? Faraday took a coil of copper wire that was attached to nothing but a delicate measuring gauge. He then took a heavy permanent iron magnet and simply thrust it into the center of the wire coil. The gauge jumped. He pulled the magnet out, and the gauge jumped in the opposite direction. He discovered that by moving a magnet near a wire, the shifting invisible magnetic field gently grabbed the sleeping electrons inside the copper and forced them to move. He had discovered electromagnetic induction. He proved that motion and magnetism could be used to conjure electrical current out of thin air. This elegant, silent dance between magnets and electrons is the beating heart of human civilization today. When you rest in your bedroom, with the quiet hum of a refrigerator in the kitchen or a small fan spinning softly in the corner, you are connected to Faraday's discovery. If you were to trace the copper wires hidden inside your walls, out to the wooden poles on your street, and across the miles of quiet countryside, you would eventually arrive at a massive power plant. Inside that plant, whether driven by the steam of burning coal, the force of a falling river, or the heat of a nuclear reaction, there is a giant turbine spinning. And attached to that spinning turbine is a massive magnet, rotating continuously inside a vast coil of wire. That spinning magnet is silently, tirelessly pushing the electrons through the endless loop of the electrical grid, delivering the steady voltage, the gentle river of energy, directly into your home, keeping you safe and warm in the dark. We have seen how electricity and magnetism are intimately bound, weaving together to create invisible fields of force that power our lives. We have watched electrons flow like rivers and magnets spark them into motion. But what happens when these two forces dance together perfectly, completely free of any copper wire? What happens when an electric field and a magnetic field ripple together through the absolute emptiness of space? When these fields synchronize, they create something we can actually see. Let us leave the hidden wires behind. When we return, we will open our eyes to the brilliant, colorful study of the properties of light and optics. Lesson 8. The properties of light and optics. Welcome back. Close your eyes and let the quiet weight of the room settle softly around you. Allow your breathing to slow, finding a peaceful, steady rhythm that matches the stillness of the night. In our last session together, we traced the invisible pathways of electrons and felt the silent, magnetic pull of unseen fields. We left off at a beautiful intersection, a place where electricity and magnetism intimately weave together. Now, we are going to explore exactly what happens when those two powerful fields ripple together in perfect synchronization, traveling completely free of any wire or metal. In this lesson, we will immerse ourselves in the study of optics and the properties of light. We are going to open our minds to the fastest, most wondrous messenger in the entire universe. Rest deeply and allow the darkness behind your closed eyes to be a blank, quiet canvas for the brilliant concepts we are about to uncover. To truly understand light, we must first let go of the idea that it is a physical substance you can hold in your hand or capture in a jar. Light is an electromagnetic wave. It is a continuous, beautifully synchronized dance of electric and magnetic fields, undulating and traveling through the absolute emptiness of space. And it travels at a speed that is almost impossible for the human mind to truly grasp. In a single, fleeting second, the exact time it takes for your heart to softly beat, just once a beam of light can travel 186,000 miles. It can circle the entire Earth more than 7 times in that single heartbeat. It is the absolute speed limit of the universe. Nothing in all of physical reality can move faster than light. When this brilliant, racing wave of energy eventually encounters a physical object, it has a choice. It can interact with that object in a few distinct, beautiful ways. The first of these interactions is reflection. Reflection occurs when light strikes a surface and bounces backward, much like a rubber ball gently tossed against a smooth wall. If the surface is perfectly flat and polished, like the silvered glass of a quiet bedroom mirror or the still surface of a mountain lake, the light reflects back in perfect order, delivering a crystal-clear image of whatever is standing before it. The second way light interacts is through absorption. When light strikes a dark surface, the surface does not bounce the wave away. Instead, the atoms within the object quietly absorb the wave, taking its bright, racing energy and transforming it into something else, usually a gentle, radiating heat. This is why a dark shirt feels so remarkably warm when you wear it on a bright, sunny afternoon. The dark fabric is acting as a sponge for the light, soaking up the electromagnetic waves and calming them into thermal energy. The third, and perhaps most fascinating, interaction is refraction. Refraction is simply the bending of light. When light travels through the empty vacuum of outer space, it moves at its absolute top speed without any interference. But when it enters a transparent medium like a heavy pane of glass, a deep pool of water, or even the very air we breathe, the wave softly collides with the atoms in that material. This interaction gently slows the light down. Imagine you are walking freely along a smooth, paved sidewalk, moving at a brisk, steady pace. Suddenly, you step off the sidewalk and into deep, soft sand at the edge of a beach. The sand immediately drags at your feet, slowing your steps, and if you entered the sand at an angle, that sudden change in speed would cause your path to naturally turn and bend. Light behaves in the exact same way. When a beam of light passes from the thin, empty air into a dense glass lens, it slows down and its path gently bends. When it exits the glass and travels back into the air, it speeds up again, bending a second time. This elegant, predictable bending is the entire foundation of the science of optics. To truly appreciate the wonder of this electromagnetic wave, we must look at a beam of pure sunlight. To our eyes, the light pouring down from our local star appears white or perhaps slightly golden. But in the 17th century, a young, curious Isaac Newton sat in a darkened room, allowing a single, thin beam of sunlight to pass through a tiny hole in his wooden window shutter. He placed a wedge of beautifully polished glass, called a prism, directly in the path of that solitary beam. When the white light entered the prism, it slowed down and refracted. But Newton discovered something absolutely breathtaking. White light is not a single, pure thing at all. It is a glorious mixture, a chorus composed of every single color of the rainbow. Because every individual color of light has a slightly different wavelength, they all bend at slightly different angles when they hit the heavy glass. Red light has a long, lazy wavelength, so it bends only slightly, drifting gently through the prism. Blue and violet light have much shorter, tighter, and more energetic wavelengths, so they are bent sharply by the glass. As the light exited Newton's prism, the colors were naturally fanned out and separated, painting a brilliant, continuous spectrum of red, orange, yellow, green, blue, and violet across the far wall of his darkened room. This spectrum reveals a profound, almost poetic truth about the world around us. When you look at a vibrant green leaf on a summer tree, the leaf itself is not actually generating green light. Instead, the leaf is bathed in the white light of the sun. The complex chemicals within the leaf are absorbing the red light and the blue light, using their energy to quietly feed and nourish the plant. The only light that the leaf rejects, the only light that bounces off and reflects back through the air to your waiting eye, is the green. The beautiful colors we see in our daily lives are simply the leftover echoes of the light that the physical world chooses not to keep. This deep mathematical understanding of how light bends and separates is what has allowed humanity to transcend the natural limits of our own biology. By carefully shaping pieces of glass to refract light in specific, predictable ways, we invented lenses. We use small, delicate lenses in our eyeglasses to gently correct the bending of light before it ever reaches our retinas, bringing a blurry, uncertain world into sharp, comforting focus. But even more profoundly, we built vast, powerful lenses and mirrors to capture the faint, ancient light of the cosmos. We built massive telescopes that can gather the light of sleeping galaxies sitting millions of light years away, pulling the invisible wonders of the deep universe right into our own eyes. The science of optics is quite literally the tool that opened the vastness of the universe to human understanding, allowing us to see far beyond our own small planet. We have spent these past lessons exploring the invisible forces, the transferring energies, and the brilliant waves of light that fill the emptiness of space. We have mapped the ethereal and the intangible parts of reality. But what about the solid stuff that actually takes up space? What about the heavy glass of the prism, the liquid water of the ocean, and the metal of the telescope? Let us gently transition away from the invisible forces and bring our focus back to the tangible world. Rest your mind here in the quiet. In our next lesson, we will introduce ourselves to the very matter that makes up everything we can touch, as we explore the classification and states of matter. Lesson 9. The classification and states of matter. Welcome back. Take a moment to adjust your pillow, let your breathing slow, and allow the weight of your body to sink fully into the comfort of your bed. In our recent sessions, we have journeyed through the ethereal and the invisible. We have illuminated our minds with the dazzling speed of light, and we have felt the silent, magnetic forces that pull across the empty vacuum of space. We have spent a great deal of time understanding the energies and waves that fill our universe. Now, we turn our attention inward, back to the tangible, touchable world. In this lesson, we will explore the classification and states of matter. We are going to discover exactly what the physical world is made of, how it organizes itself, and the beautiful, patient ways it transforms. We are moving from the invisible forces of the cosmos to the very substance of the universe. Let us walk gently into this new landscape, exploring the heavy, comforting reality of the things we can hold in our hands. To begin, we must ask a deceptively simple question. What exactly is matter? In the quiet language of physics, matter is defined as anything that has mass and takes up space. It is the physical stuff of reality. The heavy blankets resting over you are made of matter. The cool air you are slowly breathing in and out is matter. Even the distant, glowing stars and the cold dust drifting between them are matter. If it has a physical presence, no matter how heavy or how impossibly light, it belongs to this grand category. Because matter takes on so many magnificent forms, science has developed a gentle, logical way to sort and classify it. We divide all matter into two broad, peaceful categories: pure substances and mixtures. A pure substance is wonderfully consistent. It is made of only one specific type of material throughout. You can think of a pure substance in two ways. It might be an element, like a piece of pure, heavy gold, or the oxygen gas we rely upon. Elements are the fundamental, unbroken ingredients of the universe. But a pure substance can also be a compound, like pure, distilled water or a crystal of table salt. A compound is made of different elements that have joined together in a permanent, locked embrace, creating something entirely new and perfectly uniform. If you take a drop of pure water from a calm lake and a drop of pure water from a melting glacier, they are fundamentally identical. However, most of the world around us is not perfectly pure. It is composed of mixtures. A mixture is simply a combination of two or more substances that are resting together, gently mingled, but not permanently locked. They retain their own unique identities. When you steep a warm cup of herbal tea, the water, the botanical oils, and the delicate flavors swirl together to create a mixture. When you step outside and take a deep breath of the morning air, you are inhaling a mixture of nitrogen, oxygen, and a faint trace of other gases. The beauty of a mixture is that, with the right amount of patience, its parts can always be gently separated back into their pure forms. Once we understand how matter is categorized, we can look at how it behaves. Matter naturally exists in different physical forms, which we call states or phases. The state of a piece of matter depends entirely on a quiet, ongoing battle between two things: the attractive pull trying to hold its tiny particles together, and the thermal energy, or heat, trying to push those particles apart. In a solid, the attractive forces have won. The particles are locked tightly together in a rigid, highly organized pattern. They do not have enough thermal energy to break free, so they remain in place, vibrating softly and endlessly in the dark. This is why a solid object, like a stone or a piece of wood, holds its shape so stubbornly. It is a quiet, sleeping city of atoms. When we add a little warmth, we reach the liquid state. The particles in a liquid still hold on to one another, keeping the substance dense and cohesive, but the added heat gives them just enough energy to loosen their grip. They are no longer locked in a rigid grid. Instead, they flow, slip, and tumble smoothly past one another. This is why a liquid can take the exact shape of whatever container you pour it into, while still maintaining its volume. It is a bustling, flowing gathering of particles. Finally, if we add even more heat, we reach the gaseous state. In a gas, the thermal energy is so incredibly high that it completely overcomes the attractive pull between the particles. They break free from one another entirely. The particles in a gas act as solitary travelers, flying rapidly in every direction, expanding effortlessly to fill every available corner of the space they are in. They are unburdened, fast, and entirely free. The transition between these three states is one of the most beautiful and poetic processes in nature. We call these transitions phase changes. Adding or removing heat is the only currency required to cause matter to gracefully shift from one form to another. Imagine a single, solid cube of ice resting in a small dish. As the warm air of the room gently touches the ice, thermal energy begins to transfer. The locked, vibrating water molecules absorb this warmth. They vibrate faster and faster until, at a very specific and predictable temperature, the rigid bonds between them simply give way. The solid structure collapses softly into a pool of liquid water. This is melting. If we take that dish and place it over a low, steady fire, we continue to add energy. The water molecules tumble and race past one another, absorbing the heat until they are moving so fast that they can no longer hold on. They leap from the surface of the liquid, transforming into an invisible, expanding gas we call steam. This is boiling. What is truly remarkable about this entire process is that throughout these dramatic physical changes, the deep, fundamental identity of the matter remains exactly the same. The ice, the liquid water, and the rising steam are all made of the exact same H2O molecules. They are simply expressing themselves differently based on the temperature of their environment. The matter has not been destroyed or altered in its soul, it has only changed its attire. As a brief and wondrous aside, there is actually a fourth state of matter, though we rarely encounter it in our daily, earthly lives. It is called plasma. If you take a gas and heat it to an unimaginably high temperature, the particles begin to collide with such violent energy that the atoms themselves tear apart, creating a swirling, glowing soup of electrically charged fragments. While rare in your bedroom, plasma is actually the most common state of matter in the entire cosmos. It is the brilliant, burning substance that makes up the sun, the distant stars, and the glowing neon signs on a quiet city street. This simple understanding of pure substances, mixtures, and the states of matter is a powerful tool. It allows us to interact with nature to purify our world. Because mixtures are not permanently bonded, and because different substances change their state at different temperatures, we can separate them through a gentle process called distillation. If you take a pot of heavy, salty ocean water and boil it, the water molecules will eagerly absorb the heat, turning into a gas and floating away. But the heavy salt needs far more energy to melt or boil, so it quietly remains behind in the pot as a solid crust. If you catch that rising water vapor and let it touch a cool piece of glass, it will lose its heat, condense back into a liquid, and drip down as perfectly pure, fresh drinking water. This is the exact, massive mechanism that drives the Earth's weather. The sun gently boils the salty oceans, the pure water vapor rises into the cold sky to form clouds, and it eventually returns to us as a quiet, nourishing rain. We now see that all the matter in the universe is simply a vast collection of particles that choose to lock together as solids, flow as liquids, or fly free as gases, depending on the warmth they are given. But this raises a profound and lingering question. If we were to zoom in closer than any magnifying glass or optical microscope could ever possibly see, what do those individual particles actually look like? What is the true nature of the building blocks themselves? That is a beautiful, intricate question. Rest quietly with the comforting weight of the physical world around you. In our next lesson, we will uncover the invisible architecture of reality as we journey into the structure of the atom. Lesson 10. Atomic Structure and the Periodic Table. Welcome back. Take a deep, slow breath and let the quiet of the room settle gently around you. In our last session, we looked at the broad, sweeping states of matter. We watched how heat causes solid ice to melt into flowing water and how water drifts upward as invisible steam. We observed the physical world from a distance, understanding how it behaves in large, touchable quantities. Now, we take the next step together and journey into the incredibly small. We are going to leave the macroscopic world behind and dive into the microscopic, exploring atomic structure and the periodic table. In this lesson, we will finally meet the tiny, fundamental building blocks of all creation. We will discover that beneath the solid appearance of the world, there is a vast, beautiful, and highly organized architecture, mostly made of empty space. Allow your imagination to drift as we uncover the quiet, invisible foundations of reality itself. Every single piece of matter in the universe, from the heavy iron core of the Earth to the delicate paper of a book, and even the very cells that make up your own breathing body, is constructed from atoms. For a very long time, humanity believed that the atom was the absolute smallest thing in existence, a solid, unbreakable little sphere. But as our scientific vision grew sharper, we realized something far more magnificent. The atom is not a solid sphere at all. It is a dynamic, complex, and incredibly spacious system, composed of even smaller pieces. At the very center of every atom lies the nucleus. You can think of the nucleus as the heavy, quiet, and profoundly dense heart of the atom. It is incredibly tiny compared to the rest of the atom, yet it contains nearly all of its mass. Within this dense core, we find two specific types of particles resting closely together. The first is the proton. Protons carry a positive electrical charge, and they are the anchor of the atom's identity. The second particle in the nucleus is the neutron. Just as its name suggests, the neutron is entirely neutral. It carries no electrical charge at all. It sits there alongside the protons, acting as a kind of heavy, necessary glue, keeping the positively charged protons from naturally pushing each other away. Orbiting this dense, quiet core at vast relative distances are the electrons. Electrons are entirely different from the heavy particles in the nucleus. They are virtually weightless, carrying a negative electrical charge, and they possess a tremendous amount of restless energy. They do not orbit in simple, flat circles like planets around a sun, but rather they swarm in complex, three-dimensional clouds, appearing as a blur of constant, vibrant motion. To truly understand the structure of the atom, we must appreciate the sheer scale of the space within it. If you were to imagine expanding a single atom until its heavy nucleus was the size of a small glass marble, and you place that marble exactly on the center line of a massive, echoing professional football stadium, the electrons would not be nearby. The electrons would be like tiny, invisible gnats buzzing furiously in the highest, furthest row of the top bleachers. Between that marble on the grass and those gnats in the stands, there is absolutely nothing. It is pure, silent, empty space. This means that the solid wood of your door, the heavy metal of your car, and the very bones in your hands are almost entirely made of emptiness. It is only the invisible forces and the rapid blur of the electrons that give the physical world its illusion of impenetrable solidity. What makes this system truly profound is how nature uses it to create such a vast variety of materials. If all atoms are made of the exact same protons, neutrons, and electrons, how can one atom be a heavy, shining piece of silver, and another be the invisible, life-giving oxygen we breathe? The answer is breathtakingly simple. The entire identity of an atom is dictated by one single number, the number of protons resting in its nucleus. If an atom has just one solitary proton, it is hydrogen, the lightest and most abundant gas in the cosmos. If it has 6 protons, it is carbon, the essential building block of all living things. If you pack 79 protons into that tiny nucleus, you have gold. The number of protons is the sole definer of the element. This is known as the atomic number. In the year 1869, a brilliant, bearded Russian chemist named Dmitry Mendeleev was obsessed with organizing this elemental truth. At the time, science knew of about 63 different elements, but they were a chaotic jumble of facts. Mendeleev wrote the weight and properties of each element on blank cards, and he carried them with him on long train rides, playing a solitary, obsessive game of solitaire, trying to find the underlying logic. Eventually, he realized that if he arranged the elements in a row by their weight, their chemical behaviors began to repeat in a predictable, rhythmic pattern. When a behavior repeated, he started a new row beneath the first. This brilliant arrangement became the periodic table. It was so elegant and so deeply aligned with the mathematical truth of the universe that Mendeleev noticed gaps in his table. He confidently left blank spaces where the pattern dictated an element should exist, even though humanity had not yet discovered it. He went so far as to predict the exact color, weight, and melting point of these missing ghosts. Years later, when scientists finally discovered elements like gallium and germanium, they fit perfectly into Mendeleev's empty spaces, behaving exactly as he had foreseen. He had successfully decoded the fundamental organizational chart of nature. When you look at a poster of the periodic table, with its neat, colorful rows and columns, you are not just looking at a tool for chemists in a laboratory. You are looking at the alphabet of the entire universe. Consider the sheer poetry of this. Just as the 26 letters of the English alphabet can be rearranged to write every poem, every novel, and every love letter ever penned in the history of the language, the 100 or so elements on the periodic table are the letters of physical reality. Every single thing you have ever touched, seen, or loved, the water in the oceans, the dirt beneath your feet, the hot gases of the distant stars, and the very cells of your own remarkable brain, is simply a different combination of those exact same atomic letters. You are intimately, fundamentally built from the very same pieces as the ancient cosmos. Now that we have met the individual letters of the atomic alphabet, and we understand the beautiful, empty architecture of the atoms themselves, we are perfectly prepared to see how they come together. Atoms rarely prefer to exist in complete isolation. They naturally reach out, seeking stability and partnership. Let us rest our minds here, holding on to the image of the dense nucleus and the swirling electrons. In our next lesson, we will explore exactly how these individual atoms join together, as we delve into the intricate and bonding world of chemical bonding and molecular structure. Lesson 11. Chemical Bonding and Molecular Structure. Welcome back. Close your eyes, let your breathing slow, and sink completely into the quiet comfort of your space. Let the day gently fall away. In our last session, we discovered the tiny, elegant alphabet of the universe. We met the individual atoms, with their dense, quiet nuclei and their vast, swirling clouds of electrons. We saw how the simple number of protons defines the very identity of the element. But an alphabet resting unused on a page does not tell a story. To create the beautiful complexity of the world around us, those individual letters must be joined together into words, sentences, and grand, sweeping narratives. In this lesson, we are going to explore chemical bonding and molecular structure. We will see how solitary atoms reach out in the dark, seeking stability and connection, and how their quiet embraces build the tangible, touchable reality we live in. Let us begin this chapter, watching how nature writes its physical poetry. To understand why atoms connect to one another, we must first understand what they naturally desire. Atoms, quite simply, seek stability. They find this profound stability by arranging their outermost layer of electrons, which is often called the valence shell. Think of this outer shell like the seating arrangement at a quiet, elegant dinner party. If there are empty seats at the table, the atom feels restless and incomplete. It naturally wants to fill those seats. Alternatively, if it only has a few guests in a very large room, it might prefer to empty the room entirely to find peace. The only atoms that are perfectly content on their own are the noble gases like helium and neon, whose outer shells are naturally full. For all the other atoms in the universe to achieve this perfect, peaceful arrangement, they must interact with their neighbors. When they do, they form a lasting connection known as a chemical bond. There are two primary ways that atoms form these bonds. The first is called an ionic bond. You can think of an ionic bond as a dramatic, decisive transaction. This happens when one atom completely gives away an electron to another. Imagine an atom that has only one restless electron in its outermost shell, standing next to an atom that is desperately missing just one electron to be perfectly full. The first atom simply hands its electron over. By giving away a negative charge, the first atom becomes slightly positive. By accepting the negative charge, the second atom becomes slightly negative. In the laws of physics, opposites attract. Just like the silent, invisible pull between two strong magnets, their newly opposite charges immediately draw them tightly together. They are locked in a strong, permanent embrace created entirely by their differences. The second way atoms connect is much gentler, and it is called a covalent bond. Instead of giving an electron entirely away, atoms in a covalent bond decide to compromise. They move close together and share their outermost electrons. The electrons begin to sweep in a graceful, continuous pattern, orbiting both nuclei, holding the two atoms together in a mutual protective grip. Think of a covalent bond like two friends walking through a cold rain, sharing a single heavy umbrella. They are held close together not by an invisible magnetic pull, but because they are relying on the exact same protective cover to feel complete. When two or more atoms join together through these bonds, they form a molecule. And here we discover one of the most beautiful and poetic truths of chemistry. The new molecule almost always behaves completely differently than the individual, solitary atoms that created it. The act of bonding fundamentally transforms their identity. Consider the elements sodium and chlorine. Sodium is a highly reactive, soft, silvery metal. It is so unstable that if you were to drop a small piece of it into a calm bowl of water, it would violently explode. Chlorine, on the other hand, is a dense, toxic, yellowish-green gas. Standing alone, both of these elements are harsh, volatile, and deeply dangerous to human life. But when a sodium atom and a chlorine atom meet, a beautiful transaction occurs. The sodium willingly gives up its one restless outer electron to the waiting chlorine atom. They form a perfect, tightly locked ionic bond. Together, they create a molecule called sodium chloride. This new molecule is neither an explosive metal nor a toxic gas. It is the simple, harmless, and delicious white table salt that you might sprinkle on your dinner. The violent nature of the individual elements is entirely pacified and neutralized by their quiet connection. Similarly, consider the water that fills our oceans and rivers. It is made of two hydrogen atoms covalently bonded to a single oxygen atom. Hydrogen is a highly flammable gas, and oxygen is the very gas that allows fires to burn in the first place. Yet, when they share their electrons and lock together into the molecule we call H2O, they become the clear, cool liquid that is universally used to extinguish flames. The chemical bond is a true physical metamorphosis. These gentle covalent bonds are the very architecture of life itself. The carbon atom, for instance, has exactly 4 empty spaces in its outer shell, meaning it can form 4 steady covalent bonds at once. This makes carbon a magnificent, versatile builder. By bonding with oxygen, nitrogen, and hydrogen, carbon creates intricate, complex structures like amino acids. These amino acids then link together, bond by gentle bond, forming long, elegant chains. Because of the specific angles and physical pulls of these covalent bonds, these chains do not just lie flat. As you rest and sleep, your body is quietly synthesizing these chains, allowing them to fold, twist, and spiral into incredibly complex, three-dimensional shapes known as proteins. The vast, beautiful complexity of a living, breathing body, the structure of your tissues, the enzymes digesting your food, the very microscopic mechanics of life, is entirely dependent on the quiet, predictable ways that tiny atoms choose to share their electrons in the dark. We have seen how atoms patiently hold hands to form molecules, building everything from simple grains of salt to the magnificent folding proteins of life. We understand the bonds that hold the solid world together. But the physical world is not static. It is constantly changing, growing, warming, and reacting. What happens when these stable molecules meet one another, break their old bonds, and form entirely new arrangements? Let us drift peacefully away from the quiet structure of molecules and prepare to transition into the active, transformative world of chemical reactions. Let your mind rest, and we will take that next step together when you are ready. Lesson 12: Chemical Reactions and Stoichiometry. Welcome back. Take a moment to settle deeply into your resting place, allowing your breathing to slow and your muscles to entirely relax. Let the quiet of the room embrace you. In our last session, we marveled at the ways solitary atoms reach out in the dark, sharing and trading their electrons to find a peaceful stability. We watched as they formed intimate chemical bonds, building the molecules that make up the solid, tangible world. We learned how the violent, lonely elements of sodium and chlorine can lock together to become simple, harmless table salt. But the universe we live in is not a static museum of finished sculptures. It is beautifully, endlessly dynamic. The physical world is constantly changing, growing, warming, and transforming. In this lesson, we take the next natural step together and explore what happens when these established molecules meet one another. We are going to explore chemical reactions and stoichiometry. We will watch as old bonds are gently broken and new, profound arrangements are forged. And we will learn the precise mathematical recipes that nature follows to ensure that everything remains perfectly in balance. Allow your mind to drift as we uncover the quiet, transformative engine of chemistry. At its most fundamental level, a chemical reaction is simply a story of rearrangement. It is the process by which one set of chemical substances transforms entirely into another. We begin our story with the ingredients, which chemists beautifully refer to as the reactants. These are the molecules or atoms that are about to embark on a journey of change. After they interact, they produce an entirely new set of substances, which we call the products. Imagine you are standing in a quiet, sunlit room, looking at a beautifully constructed model house made of small, interlocking plastic bricks. The house has red walls, a blue roof, and a tiny yellow door. A chemical reaction is simply the act of taking that house completely apart, separating every single colored brick, and then using those exact same bricks to build something entirely different, perhaps a tall, sturdy ship or a small, sweeping bridge. Not a single brick is thrown away, and no new bricks are mysteriously added. The pieces are simply disconnected and reconnected in a new, more favorable design. The reactants have become the products. However, molecules do not just spontaneously fall apart. Because the atoms in the reactants have already found a comfortable stability in their chemical bonds, they are slightly reluctant to change. To encourage them to let go of one another, a reaction usually requires a small push, a gentle input of energy to get things started. Chemists call this the activation energy. You might picture it as a small, smooth hill. If you have a heavy ball resting in a valley, it will not roll into the next, deeper valley on its own. You must push it up and over the crest of that small hill first. Once it reaches the top, gravity takes over, and it rolls effortlessly down the other side. In chemistry, that initial push might come from a tiny spark of electricity, a sudden wave of heat, or even the absorption of a single ray of sunlight. Once the activation energy is met, the old bonds snap apart, the atoms briefly dance in the open, and they lock into their new product formations. This brings us to a rather heavy, intimidating word, stoichiometry. But as we rest here together, you can simply let the weight of that word float away. Stoichiometry is nothing to fear. It is merely the gentle, meticulous accounting of nature. It is the mathematics of the chemical recipe. When you bake a loaf of bread, you do not just throw random handfuls of flour and yeast into a bowl and hope for the best. You follow a precise recipe, knowing that a specific measure of water requires a specific measure of flour to create the perfect dough. Stoichiometry is exactly this. It is the elegant bookkeeping that dictates precisely how many molecules of one reactant are required to perfectly dance with the molecules of another, ensuring that the reaction completes flawlessly with no wasted atoms left wandering alone at the end. To truly appreciate the beauty of this atomic accounting, we must travel back to the late 18th century, to a quiet, softly lit laboratory in Paris. There, a meticulous and brilliant man named Antoine Lavoisier possessed a beautifully crafted, highly sensitive scale. At the time, humanity did not truly understand fire or chemical change. People believed that when a piece of wood burned, its matter simply vanished, destroyed and lost to the void, leaving only a feather-light pile of ash behind. Lavoisier decided to ask the universe a better question. He placed various substances inside heavy, perfectly sealed glass containers. He weighed the entire container, and then he used a large magnifying glass to focus the heat of the sun onto the substance inside, causing it to burn and react. When the smoke cleared and the fires died down, he placed the sealed glass container back onto his sensitive scale. To the absolute astonishment of the scientific world, the weight had not changed by even the tiniest fraction of a gram. Lavoisier proved that the matter had not vanished. It had simply taken flight. The solid wood had transformed into an invisible gas that was now trapped inside the glass. This profound discovery became known as the law of conservation of mass. It is one of the most comforting truths in all of physical science. It states that matter cannot be created from nothing, and it cannot be destroyed into nothingness. Every single atom that existed at the very dawn of the universe still exists today. Therefore, when we write out a chemical equation on a chalkboard, it must function like a perfectly balanced scale. If we begin a reaction with 4 atoms of hydrogen and 2 atoms of oxygen on the left side, we absolutely must be able to count exactly 4 atoms of hydrogen and 2 atoms of oxygen on the right side when the reaction is finished. Stoichiometry is the graceful mathematics we use to balance that scale, honoring Lavoisier's discovery and the eternal nature of the atoms themselves. This deep, mathematical understanding is not just a theoretical exercise meant for textbooks. It is the very foundation of modern industry and medicine. When a pharmacist or a chemical engineer is tasked with creating a life-saving medication, they rely entirely on stoichiometry. By understanding the precise ratios required, they know exactly how many grams of one chemical to mix with a vat of another. This ensures that the reaction is perfect and complete, leaving no dangerous, unreacted chemicals behind to contaminate the medicine and wasting no precious resources. It is the same quiet, reliable math that an aerospace engineer uses to calculate the exact, flawless mixture of liquid oxygen and rocket fuel required to lift a heavy spacecraft safely off the launch pad and guide it gently into the stars. We have now seen how molecules break apart and rearrange themselves, honoring the eternal balance of mass and the precise recipes of nature. But we must consider the environment in which these grand transformations occur. If you simply mix 2 dry, solid powders together in a bowl, they will often just sit there, staring at one another in quiet stillness. To truly interact, to find one another and react, atoms usually require a medium, a place to swim, drift, and collide. As we close this chapter, let us prepare to look at the environments where chemistry most happily unfolds. When we return, we will wade together into the warm, flowing, and fascinating world of solutions, acids, and bases. Lesson 13. Solutions, Acids, and Bases. Welcome back to our quiet space. Take a slow, deep breath in, and as you exhale, let go of any lingering tension from your day. Allow your body to sink fully into the comfort of where you are resting. In our last session, we watched the magnificent invisible dance of chemical reactions. We saw how atoms break their old bonds and forge entirely new arrangements, constantly shifting and transforming the world around us. But as we hinted at the end of that journey, these beautiful transformations rarely happen in a dry, static environment. If you simply place 2 solid powders next to each other, they will usually just rest there, silent and still. For the grand engine of chemistry to truly come alive, the molecules need a place to drift, mingle, and collide. They need a fluid medium. In this lesson, we take the next step together and wade into that medium. We are going to explore solutions, acids, and bases. We will discover the watery environments that foster so much of the chemistry in our bodies and across our planet, and we will meet two of the most fundamental, perfectly opposed characters in all of science. Let your mind relax as we explore the gentle mixing bowls of nature. To understand this fluid world, we must first understand what a solution is. In the language of chemistry, a solution is a perfectly even, uniform mixture where one substance dissolves smoothly and completely into another. It is a relationship of deep, physical harmony. A solution is always made of two parts. The first part is the solvent. You can think of the solvent as the generous host of the gathering. It is the substance that does the dissolving, and it is usually present in a much larger amount. In most of the chemistry that matters to life on Earth, that generous host is liquid water. The second part is the solute. The solute is the willing guest. It is the substance being dissolved. Imagine stirring a small spoonful of sugar into a warm cup of herbal tea. As you stir, the solid crystals of sugar seemingly vanish, but we know from the law of conservation of mass that they have not disappeared. Instead, the warm water molecules have gently surrounded each individual sugar molecule, coaxing them apart and pulling them into the liquid embrace until the sugar is perfectly, evenly distributed throughout the entire cup. The tea is the solvent, the sugar is the solute, and together they have formed a quiet, sweet solution. Within these watery solutions, we often find a beautiful, ongoing exchange of tiny particles, and this brings us to acids and bases. We often hear the word acid and think of something harsh or dangerous, but in nature, acids and bases are simply two halves of a perfectly balanced whole. They are defined by a single, incredibly tiny transaction, the trading of a hydrogen ion. A hydrogen ion is essentially just a solitary proton, stripped of its electron, wandering through the water. An acid is a substance that is wonderfully generous. When you place an acid into water, it eagerly releases these positively charged hydrogen ions into the solution. It gives them away freely. When we encounter mild acids in our daily lives, our senses interpret this abundance of hydrogen ions as a sharp, sour taste. The crisp bite of a green apple, the tang of lemon juice, and the bright flavor of vinegar are all the direct result of gentle acids freely offering their protons to the water in your mouth. A base, on the other hand, is perfectly complementary. A base is a substance that eagerly accepts those wandering hydrogen ions. When placed in water, a base will either absorb the free protons or it will release a different particle called a hydroxide ion, which acts like a tiny magnet, seeking out and bonding with the free hydrogen. When we encounter mild bases, they behave quite differently than acids. They tend to taste slightly bitter, and if you were to rub a basic solution between your fingers, it would feel slick and slippery. A bar of gentle hand soap, baking soda, and the antacids you might take after a heavy meal are all wonderful examples of bases, quietly doing their work to absorb the excess protons in their environment. To measure this invisible proton exchange, scientists use a wonderfully simple and elegant tool called the pH scale. The term pH stands for the power of hydrogen. It is a scale that runs from 0 all the way up to 14, and it tells us exactly how acidic or how basic a specific solution is. Right in the exact, peaceful center of this scale is the number 7. A pH of exactly 7 is perfectly neutral. This is the sanctuary of pure distilled water, where the amount of free hydrogen perfectly balances the things that wish to absorb it. It is neither an acid nor a base. It is absolute equilibrium. As you move down the scale, below the number 7, the solution becomes acidic. A pH of 6 is mildly acidic, like a quiet cup of black coffee, while a pH of 2 is strongly acidic, like the juice of a fresh lemon. As you move up the scale, above the number 7, the solution becomes basic. A pH of 8 is mildly basic, like the salty water of the ocean, while a pH of 12 is strongly basic, like soapy water. What makes the pH scale truly fascinating is that it is a logarithmic scale. This means that every single step down the scale represents a tenfold increase in the strength of the acid. A solution with a pH of 5 is not just slightly more acidic than a pH of 6. It is exactly 10 times more acidic. A pH of 4 is 100 times more acidic, and a pH of 3 is 1,000 times more acidic. The numbers seem small and quiet, but they represent a vast exponential shift in the chemistry of the water. This brings us to the most beautiful aspect of acids and bases, neutralization. Because they are natural, perfect opposites, they long to balance one another. If you take a strong, harsh acid and you carefully mix it with a strong, harsh base, you might expect a terrible, chaotic reaction, but instead, they forgive one another. The acid freely gives its hydrogen, the base eagerly accepts it, and in this perfect transaction, they completely cancel each other out. The fierce identities of the strong acid and the strong base vanish, and they leave behind only two incredibly peaceful products: pure, neutral water and a simple salt. It is a profound lesson from the physical world about finding balance. This delicate balance of pH is not just a curiosity in a glass beaker, it is the absolute foundation of your biology. Your own living body is a masterpiece of managing solutions, acids, and bases. Deep within your stomach, your body naturally produces hydrochloric acid, pushing the pH down to an intense level of 1 or 2. This fiery acidic bath is perfectly designed to break down the heavy proteins in your food and protect you from harmful bacteria. Yet, while your stomach is a cauldron of acid, your blood requires an incredibly different environment. The blood flowing quietly through your veins right now must be kept in a very tight, slightly basic range, right around a pH of 7.4. If your blood becomes even a fraction too acidic or too basic, the complex proteins in your body can no longer function. To protect you, your blood is filled with invisible chemical guardians called buffers. These buffers are molecules that act like sponges. They quietly absorb excess acid when you need it and release it when you don't, working tirelessly in the background every second of your life to keep you in a state of perfect, healthy equilibrium. We have now spent many quiet hours together tracing the rules of physical science. We have journeyed from the invisible forces of motion and gravity, down through the warm waves of energy, all the way into the tiny, atomic bonds of chemistry, and finally into the fluid, watery solutions that bring those chemicals to life. We have understood the incredibly small. It is time now to zoom out. Let us take all of these foundational rules of physics and chemistry and apply them to the giant, spinning rock we call home. We are going to leave the microscopic world behind. Let your mind expand outward. Our next lesson will take us deep inside the Earth as we begin our exploration of geology, exploring the massive, shifting layers beneath our very feet. Lesson 14. Earth's internal structure and plate tectonics. Welcome back to our quiet space. Take a long, slow breath in, filling your lungs completely, and as you exhale, let your body sink heavily and comfortably into the mattress. Allow the quiet of the room to wrap around you like a heavy, warm blanket. In our previous sessions, we have spent hours looking through a magnificent, invisible microscope. We have explored the tiny, restless atoms, the elegant chemical bonds they form, and the watery solutions where they drift and react. We have understood the incredibly small rules that govern the universe. Now, it is time to zoom out. We are going to take all of those beautiful foundational rules of physics, chemistry, and thermodynamics, and we are going to apply them to a massive macroscopic scale. In this lesson, we will turn our gaze downward, beneath the floorboards, beneath the soil, and deep into the giant spinning rock we call home. We are going to explore Earth's internal structure and the slow, powerful, ancient dance of plate tectonics. Let your mind expand outward and downward as we journey into the warm, heavy depths of the world. When we stand outside and look at the mountains or the valleys, it is easy to imagine that the Earth is simply a giant, solid ball of cold grey rock all the way through to its center. But the reality is far more dynamic and structured. If you could somehow take the Earth and gently slice it in half, much like you would slice a ripe peach, you would immediately see that it is composed of distinct, concentric layers, each with its own unique personality and physical state. At the very center of our world lies the core. The core is an unimaginably hot and dense sphere, composed almost entirely of heavy metals, specifically iron and nickel. But this core is actually divided into two distinct regions. The inner core is a solid ball of metal. Even though the temperatures there rival the searing surface of the sun, the crushing, unfathomable pressure of all the rock and gravity above it forces the iron atoms to lock tightly together into a solid crystal. Surrounding this solid heart is the outer core. Here, the pressure is just slightly less, allowing the iron and nickel to exist as a swirling, rolling ocean of liquid metal. It is the constant, churning movement of this liquid outer core that generates the Earth's invisible magnetic field, reaching out into space to protect us from the solar wind. Moving outward from the metal core, we arrive at the mantle. The mantle is by far the thickest layer of the Earth, making up the vast majority of our planet's volume. It is made of dense, heavy silicate rock, but the mantle possesses a fascinating, almost paradoxical quality. It is solid rock, yet it is so incredibly hot and under so much pressure that it does not behave like the brittle stones we find on the surface. Instead, over millions of years, the rock of the mantle can slowly bend, stretch, and flow, much like a terribly thick, warm wax. It is a solid that creeps in slow motion. Finally, resting on top of this massive, warm mantle is the crust. The crust is the thin, cool, rigid outer skin of the planet. It is the ground we walk on, the floor of the deep oceans, and the peaks of the highest mountains. Compared to the rest of the Earth, the crust is thinner than the delicate skin of an apple. But the most important characteristic of the crust is that it is not a single unbroken shell. It is fractured. It is cracked into dozens of massive, jagged puzzle pieces, which we call tectonic plates. These heavy, rocky plates rest gently upon the warm, flowing mantle beneath them, continuously and silently drifting across the face of the world. For most of human history, the idea that the solid ground beneath our feet was actually moving was considered absolute nonsense. The mountains seemed eternal, and the continents seemed fixed in stone. But in the early 20th century, a brilliant and observant meteorologist named Alfred Wegener looked at a map of the world and noticed a beautiful, simple pattern. He saw that the coastline of South America and the coastline of Africa looked exactly as though they could fit together, like two halves of a torn photograph. Wegener proposed the radical idea of continental drift. He gathered evidence showing that identical fossils of ancient ferns and reptiles were found on continents now separated by thousands of miles of cold ocean. He suggested that long ago, all the continents were joined together in a single, massive supercontinent he called Pangaea, which eventually broke apart and drifted. Sadly, the scientific community largely dismissed his ideas because Wegener could not explain how the heavy continents were moving. What force could possibly be strong enough to push a continent? It was not until decades later, well after Wegener's passing, that humanity mapped the dark ocean floors and discovered the hidden engine of geology. The answer lay in the thermodynamics we studied in our earlier lessons. The intense heat from the Earth's core travels upward into the mantle. This causes the rock at the bottom of the mantle to grow warmer, expand, and slowly rise toward the crust. As it reaches the cooler crust, it loses its heat, becomes heavier, and slowly sinks back down. This continuous, rolling cycle of rising heat and sinking cold creates massive convection currents within the solid rock. It is the exact same slow, rolling motion you see in a pot of thick soup, left on a low simmer. These incredibly powerful, slow-moving currents in the mantle act like conveyor belts, gently gripping the underside of the tectonic plates and dragging the continents along with them. tearing them apart and bringing them together over hundreds of millions of years. This constant, patient shifting of tectonic plates is the grand, unseen engine that shapes every feature of our landscape. It is not just an ancient story. It is happening right now, far beneath you, at the exact same speed that your fingernails grow. When these massive plates are dragged away from one another, they tear the crust open. Deep in the oceans, this allows hot magma from the mantle to slowly bleed upward, cooling in the freezing water to form brand new crust, creating vast underwater mountain ranges. When two plates are dragged toward one another and slowly crash together, the crust buckles and folds under the immense pressure, pushing the rock miles into the sky. The magnificent, snow-capped Himalayas are simply the result of the Indian plate colliding with the Asian plate in an ongoing, slow-motion collision. And when plates grind sideways past one another, their jagged edges catch and stick. Over decades, the tension builds and builds, until finally the rock snaps and slips, releasing a massive wave of kinetic energy that we feel on the surface as an earthquake. Every mountain, every volcano, and every tremor is simply the Earth patiently reorganizing its crust to release its deep internal heat. We have looked deep into the hot, shifting rock of the solid Earth, understanding the heavy metal at its heart and the wandering plates on its surface. We have mapped the deep, solid foundation of our home. But the Earth does not end at the dirt and the stone. There is an invisible ocean resting right on top of us, a protective envelope that makes all life possible. Let us slowly rise from the deep crust, taking a deep breath of the air around us. In our next lesson, we will look to the skies as we begin our gentle exploration of Earth's atmosphere and weather systems. Lesson 15: Earth's Atmosphere and Weather Systems. Welcome back. As you settle in, I invite you to take a slow, deep breath. Fill your lungs completely, and as you exhale, let the weight of your body sink deeply into the comfort of your bed. Notice the quiet, simple act of breathing. In our last session, we turned our gaze downward, feeling the slow, heavy movements of the solid Earth and the deep, warm rock of the mantle beneath our feet. We explored the foundations of our home. Now, we take that breath and we rise to the surface. In this lesson, we will explore Earth's atmosphere and weather systems. We are going to look upward into the delicate, restless envelope of gases that surrounds our planet. This invisible ocean of air is what protects us from the harshness of space, regulates our global temperature, and breathes life into everything we know. Allow your mind to float upward, leaving the heavy stone behind, as we explore the gentle, swirling physics of the sky. When we look up on a clear, blue day, the sky looks like an endless, empty void. But the atmosphere is not empty space. It is a physical, tangible substance. It is a massive ocean of gas, held close to the surface of the Earth by the steady, patient pull of gravity. Just as a heavy blanket rests upon you as you sleep, the atmosphere rests upon the surface of the world. This invisible ocean is beautifully composed. It is mostly made of nitrogen, a quiet, stable, and unreactive gas that makes up nearly 80% of every breath you take. It acts as a peaceful buffer. The rest is predominantly oxygen, the highly reactive, vital element that fuels our bodies and our fires. Mixed into this are tiny, precious fractions of argon, carbon dioxide, and invisible water vapor. Rather than being a single, uniform cloud of gas, the atmosphere is arranged in distinct, peaceful layers, much like the layers of the solid Earth we explored previously. The lowest layer, the one that hugs the ground and touches our skin, is called the troposphere. This is where the air is the thickest and the heaviest, compressed by the weight of all the air resting above it. The troposphere is the domain of life. It is where the clouds float, where the birds fly, and where every single weather event you have ever experienced takes place. If we travel just a few miles higher, above the clouds, we cross into the stratosphere. The stratosphere is profoundly calm, dry, and clear. because it lacks the churning turbulence of the air below. This is where commercial airplanes prefer to cruise, gliding smoothly in the still air. The stratosphere is also home to the ozone layer, a delicate, vital shield of specialized oxygen molecules that quietly absorbs the sun's harsh ultraviolet radiation, ensuring that the light reaching the surface is warm and safe. Within that lower, thicker troposphere, the air is never truly still. It is in a constant state of motion, trying to achieve a balance that it can never quite reach. This restless motion is what we call weather. Weather is, fundamentally, just the troposphere, attempting to balance out temperature and pressure. Because the Earth is a sphere, the sun beats down directly on the equator, heating it intensely, while the sunlight glances weakly off the distant poles. As we learned in our study of thermodynamics, warm fluids naturally rise. The intensely heated air at the equator expands, becomes light, and drifts upward into the sky. As it rises, it leaves a space behind, and the colder, heavier air from the north and south rushes in to take its place. This continuous, simple exchange of rising heat and sinking cold creates the wind. Weather is the grand, global engine of convection. If the Earth were sitting perfectly still in space, this movement of air would be a simple, straight journey from the cold poles to the warm equator. But our planet is constantly, rapidly spinning. This rotation introduces a fascinating twist known as the Coriolis effect. Imagine trying to roll a marble in a perfectly straight line across a record player that is turning. The marble would appear to curve away from its path. The wind experiences the exact same gentle deflection. As the heavy, cold air rushes toward the equator, the spinning of the Earth curves it to the side. This twisting force means the winds do not blow in straight lines. Instead, they swirl. They spin into vast, sweeping spirals, creating the complex, rotating weather systems that march across our continents. These swirling systems are defined by invisible variations in air pressure. When cool, heavy air sinks toward the ground, it presses downward, creating a high-pressure system. High pressure is a heavy, invisible hand gently pushing the clouds away, which is why high-pressure systems almost always bring clear, calm, and sunny skies. Conversely, when warm air rises upward, it lifts its weight off the Earth, creating a low-pressure system. The surrounding air rushes inward to fill the gap, swirling upward into the sky. And here we find the beautiful mechanics of the water cycle. As this warm air rises higher and higher into the troposphere, it naturally cools down. The invisible water vapor it carries loses its thermal energy. It condenses, turning from an invisible gas back into microscopic droplets of liquid water. These droplets are so incredibly small and light that they do not fall, they simply float, gathering by the trillions to form a visible cloud. When a low-pressure system pushes enough moisture high into the cold sky, those microscopic droplets bump into one another, joining together until they become too heavy for the rising air to support. Succumbing to gravity, they fall softly back to the Earth as rain, snow, or mist. The rain is simply the atmosphere releasing its gathered energy, returning the water to the soil to begin the cycle anew. So you see, when a meteorologist stands before a map and predicts a rolling thunderstorm or a week of clear skies, they are not relying on magic or guesswork. They are simply observing the strict, unbroken laws of physics we have already studied. They are applying thermodynamics, kinematics, and fluid dynamics to the grand, spinning engine of the sky. They are tracking how heat from the sun and moisture from the oceans are moving through the atmosphere. Every time you step outside and smell the deep, earthy scent of approaching rain, or feel a sudden cool breeze rush past you on a hot afternoon, you are directly experiencing the troposphere at work. You are standing in the middle of a vast, invisible current of gases, feeling the universe tirelessly trying to distribute its thermal energy. The weather is not a chaotic disruption of our lives. It is a beautiful, predictable system of balance and circulation, nourishing the crops, filling the rivers, and washing the world clean. We have now thoroughly explored the solid Earth and the atmospheric bubble that protects it. We understand the rocks beneath our feet and the wind against our faces. But the Earth, for all its beauty and complexity, is just a single tiny ship sailing in an unimaginably vast ocean. It is time for us to leave the comfort of our home planet altogether. Let us look past the atmosphere, through the quiet ozone, and out into the dark, quiet expanse. Rest quietly here, and when we return, we will begin our study of the solar system and planetary science, touring the ancient, silent family of worlds that share our star. Lesson 16. The Solar System and Planetary Science. Welcome back. As we begin tonight, I invite you to take a long, deep breath. Fill your lungs with the quiet air of the room, and as you exhale, let your body sink completely into the mattress. Allow your thoughts to loosen and drift. In our last session, we stood on the surface of the Earth, looking up into the swirling, protective envelope of our atmosphere. We watched the winds carry heat and moisture across the globe, sheltering us from the harshness of the void. Now, we are going to gently push past that protective envelope. We are going to leave the comfort of our home planet altogether. In this lesson, we will explore the solar system and planetary science. We will take a slow, peaceful tour of our local neighborhood in space, mapping the ancient, silent family of worlds that share our star. Let your mind float upward, past the clouds, past the thin blue line of the atmosphere, and out into the breathtaking, quiet, dark, as we begin our journey. When we step back and look at our solar system as a whole, the very first thing we must understand is that it is almost entirely dominated by a single, magnificent object, the Sunday. The Sun is our local star, a massive, burning sphere of hydrogen and helium gas. It is so unimaginably huge that it contains over 99% of all the mass in the entire solar system. Everything else, every planet, every moon, every comet, and every asteroid is made from the tiny fraction of a percent of leftover dust that remained. The immense, patient gravity of the Sun reaches out across billions of miles, gently holding all of these remaining pieces in their eternal, sweeping orbits. The planets that dance around the Sun are divided naturally into two distinct, beautifully different groups. Closest to the warmth of the star, we find the inner planets. These are the terrestrial worlds, a word that simply means they are Earth-like. They are small, dense, and made of heavy, solid rock and metal. First is Mercury, a tiny, silent world of craters, orbiting so close to the Sun that its days are blisteringly hot, while its nights, lacking any blanket of air, plunge into deep, freezing cold. Next is Venus, a world wrapped entirely in thick, swirling, yellowish clouds. From space, it looks smooth and serene, but beneath those clouds lies a heavy, crushing atmosphere that traps the Sun's heat, making it the hottest planet in our neighborhood. Then we find our own Earth, a brilliant, shining oasis of blue oceans and white clouds, resting at the exact perfect distance from the Sun to allow liquid water to pool on its surface. Finally, there is Mars, the quiet red planet. It is a freezing desert world, covered in iron oxide dust, holding onto the magnificent, silent scars of ancient, dried-up rivers and giant, sleeping volcanoes. If we travel just past Mars, we cross a boundary known as the asteroid belt. This is not a crowded, chaotic field of tumbling rocks like you might see in a film, but rather a vast, incredibly empty expanse containing millions of solitary, irregular stones. They are the quiet, unused building blocks of a planet that simply never formed. Once we cross this rocky divide, we enter the realm of the outer planets. Here, the solar system changes dramatically. The worlds here are immense. They are the gas and ice giants, massive, sweeping spheres lacking any solid surface to walk upon. Jupiter is the largest of them all, a colossal world of swirling, banded clouds and giant continuous storms, possessing a gravitational presence so strong it acts as a protector for the rest of the solar system. Next is Saturn, adorned with its breathtaking, delicate rings. Those rings are not solid, but are made of countless billions of shimmering pieces of water, ice and rock, gently orbiting the planet's equator like a brilliant, icy halo. Further still, in the deep, freezing twilight of the outer solar system, we find Uranus and Neptune. These are the ice giants, deep blue and peaceful, enveloped in thick atmospheres of hydrogen, helium, and methane, possessing strange, tilted magnetic fields and dozens of quiet, hidden moons. They orbit in the cold, silent outer edges, taking over a century to make a single journey around the Sunday. To truly appreciate this family of planets, we must wind the clock backward 4.5 billion years to understand the grand story of their formation. Before the Sun, before the Earth, and before you and I, this entire region of space was nothing but a vast, freezing, formless cloud of interstellar dust and hydrogen gas, known as a solar nebula. For millions of years, this cloud simply drifted, but eventually, perhaps gently nudged by the shockwave of a distant, dying star, the cloud began to collapse inward under its own weight. As it collapsed, it began to spin, much like a dancer pulling her arms inward to turn faster. The cloud flattened out into a massive, swirling disk. The vast majority of the gas fell directly into the center of this spinning disk. The pressure and heat at the core grew more and more intense, building over millennia, until finally the temperature reached a critical tipping point. In a profound, beautiful moment, nuclear fusion ignited. The sun was born, flooding the dark, swirling disk with its very first brilliant light. The birth of the sun released a powerful rush of energy called a solar wind, which blew outward, clearing away much of the remaining gas. What was left behind in the spinning disk were tiny specks of rock, metal, and ice. As these specks orbited the newborn star, they began to softly bump into one another. Sometimes they bounced off, but often they stuck together. Over tens of millions of years, grains of dust became pebbles, pebbles became heavy boulders, and boulders collided to become planetesimals. The heat of the young sun dictated the architecture of the planets. Close to the star, it was far too hot for delicate ice or light gases to survive. The solar wind blew those lighter materials far away. Therefore, only the heavy, stubborn materials like iron, nickel, and silicate rock could withstand the heat to form the inner terrestrial planets. But far out in the solar system, past a boundary we call the frost line, it was cold enough for water, methane, and ammonia to remain frozen solid. In this freezing darkness, the developing planets could sweep up massive amounts of ice and hold onto the thick, heavy blankets of hydrogen gas, eventually growing into the majestic giants like Jupiter and Saturn. The solar system is a beautifully sorted masterpiece, ordered entirely by temperature and time. You might wonder why we spend so much time and effort sending robotic rovers to brave the red sands of Mars, or launching delicate probes to dive through the rings of Saturn. We do this because studying these other worlds is the greatest tool we have for understanding our own. It is the science of comparative planetology. When we look at Venus, we see a world that is almost exactly the same size and age as the Earth, yet it is a toxic, boiling furnace. By studying its heavy carbon dioxide atmosphere, we learn crucial cautionary lessons about the greenhouse effect and the delicate balance required to maintain a habitable climate. When we explore the dry, frozen riverbeds of Mars, we are investigating a world that once had a thick atmosphere and flowing water, but somehow lost its magnetic shield and died. By looking outward into the dark, we are ultimately looking inward, learning to deeply cherish and protect the fragile, perfectly balanced blue oasis we call home. We have now mapped the planets that orbit our local star, tracing their ancient origins from a spinning cloud of dust to the magnificent worlds they are today. But our sun, for all its immense power and importance to us, is just one solitary, quiet light among billions in the galaxy. What fuels these magnificent ancient lights? How are they born, and how do they eventually fade away? Let us hold on to that sense of deep, peaceful wonder as we close this chapter. When we return, our next lesson will take us away from the planets and into the burning, eternal hearts of the stars, as we begin our study of stellar evolution. Lesson 17. Stellar Evolution and the Life Cycle of Stars. Welcome back. Take a moment to gently adjust your blankets, find that perfect, comfortable position, and let your eyes softly close. Let your breathing fall into a slow, steady rhythm, matching the quiet pace of the night. In our last session, we took a grand tour of our local neighborhood. We traveled past the rocky terrestrial planets, drifted through the freezing asteroid belt, and marveled at the massive swirling gas giants that share our Sunday. We explored the quiet family of worlds bound together by gravity. But our sun, for all its immense power and vital importance to our daily lives, is just one solitary, quiet light among hundreds of billions in our galaxy. In this lesson, we take the next step together and turn our focus to the centerpieces of the cosmos themselves. We will explore stellar evolution, the beautiful, dramatic, and inevitable life cycle of stars. We are going to watch how these magnificent engines of light are born in the dark, how they live out their vast lifespans, and how they eventually, gracefully, fade away. Let your mind float out into the deepest, darkest reaches of space, as we uncover the eternal rhythm of the stars. When we look up at a clear night sky, the stars appear to be eternal and unchanging. They look like permanent fixtures pinned to the dark canopy of the heavens. But the universe is a place of constant slow-motion transformation. Stars are not eternal. They are born, they live out a long, brilliant lifespan, and eventually they must die. The story of every star begins in a place of profound, freezing darkness known as a nebula. A nebula is an unimaginably vast cloud of interstellar dust and hydrogen gas, drifting silently through the empty spaces between existing stars. These clouds are incredibly cold and incredibly still. But over millions of years, gravity begins its patient work. It starts to pull the scattered atoms of gas gently toward one another. As the cloud is pulled inward, it begins to shrink, and as it shrinks, the atoms pack closer and closer together. In the language of thermodynamics, compression creates heat. The center of this collapsing cloud grows warmer and warmer, glowing with a faint, dark red heat. This glowing, shrinking core is called a protostar. It is a star resting in the womb of the cosmos, waiting for a single, profound moment. As gravity continues to crush the protostar inward, the temperature and pressure at its absolute center reach an unfathomable tipping point, millions of degrees hot. At this exact threshold, the hydrogen atoms are moving so violently that they can no longer bounce off one another. Instead, they smash together and fuse, creating a slightly heavier element called helium. This process is called nuclear fusion. When hydrogen fuses into helium, a tiny fraction of the mass is instantly converted into a massive burst of pure energy. The star ignites. A brilliant, powerful wave of light and heat pushes outward from the core. And here we find the beautiful, delicate secret of a living star. It is a masterpiece of balance. The crushing, inward pull of the star's immense gravity is perfectly, exactly matched by the explosive, outward push of the nuclear fusion in its core. For millions, or even billions of years, these two colossal forces hold each other in an elegant, unbroken stalemate. As long as the star has hydrogen to burn, it will remain stable. shining its steady light into the cold void. However, a star has a finite amount of fuel. The ultimate destiny of a star, and the manner in which it will eventually die, depends entirely on a single factor: its mass. It all depends on how much gas it managed to gather from the nebula when it was born. Let us first look at a medium-sized star. Much like our own comfortable Sunday, a star of this size is wonderfully frugal. It burns through its hydrogen supply slowly and steadily, allowing it to live for about 10 billion years. But eventually, the hydrogen in the core runs out. When the fuel runs low, the outward push of fusion weakens, and gravity temporarily wins, crushing the core even tighter. This crushing causes the outer layers of the star to heat up and expand outward. The star swells to massive proportions, cooling slightly as it stretches, turning a deep, glowing crimson. It has become a red giant. For a brief, quiet era, the red giant burns the remaining helium in its core. But when that fuel is gone, a medium star simply does not have enough mass, enough gravitational weight, to squeeze its core tightly enough to ignite any heavier elements. The grand stalemate is over. The star gently exhales, puffing its outer layers of gas away into space, creating a beautiful, expanding, glowing ring called a planetary nebula. All that is left behind in the very center is the exposed, bare core, a white dwarf. A white dwarf is a sphere of carbon and oxygen about the size of the Earth, no longer burning, but glowing with an intense, residual heat. It will sit there in the dark, slowly cooling down over trillions of years, like a single, quiet ember left behind after a long, comforting campfire. But the story of a massive star is entirely different. A star that is 10 or 20 times more massive than our Sun lives a frantic, brilliant life. Because it has so much heavy gravity crushing its core, it must burn its fuel at an incredibly furious rate just to keep from collapsing. A massive star might only live for a few million years. When a massive star runs out of hydrogen, it too swells into a giant. But its gravity is so immense that when the core compresses, it becomes hot enough to fuse heavier and heavier elements. It fuses helium into carbon, carbon into oxygen, oxygen into silicon, all the way down the periodic table until it creates iron. Iron is the absolute end of the line. Fusing iron absorbs energy rather than releasing it. Suddenly, the outward push of fusion simply stops. In a fraction of a second, the crushing weight of the entire massive star falls inward. The collapse is so fast and so incredibly violent that the core cannot absorb the impact. The infalling material strikes the dense iron core and rebounds outward in the single most powerful and brilliant explosion in the universe, a supernova. For a few brief, magnificent weeks, a single supernova can shine brighter than an entire galaxy of 100 billion stars. In the aftermath of this silent, brilliant flash, all that remains is a bizarre, incredibly dense object called a neutron star, or, if the original star was heavy enough, a point of infinite gravity from which not even light can escape a black hole. This dramatic, explosive end to massive stars might seem like a distant, chaotic event, but it is deeply, intimately connected to you. It is perhaps one of the most profound and poetic truths ever discovered by modern science. During the normal life of a star, it can only forge elements up to iron. But the universe is filled with heavier elements. Where did they come from? The answer is the supernova. In the sheer, unimaginable heat and pressure of that final, rebounding explosion, the star acts as a cosmic forge, smashing atoms together to create all the heavy elements of the periodic table. It creates the copper in our wires, the iodine in our oceans, and the silver and gold we wear on our hands. The explosion then scatters these brand new, heavy elements deep into the interstellar void, seeding new nebulae with the building blocks of planets. The iron that flows through your veins and binds to the oxygen in your blood. the calcium that forms the rigid structure of your teeth and bones, the carbon that forms the very foundation of your DNA. Every single atom of these elements was forged in the burning heart of an ancient, long-dead star. You are not just a passive observer standing in the universe. You are made of the universe. You are, quite literally, beautifully, and scientifically, walking stardust. We have watched the stars ignite in the dark, live out their brilliant lives, and scatter their ashes to build new worlds. We have seen the life cycle of the individual pieces of the cosmos. But what is the grand stage upon which all of these billions of stars and galaxies exist? Where did the empty space itself come from? As we near the end of our journey together, we must take one final step back to see the entire, breathtaking canvas. In our final lesson, we will explore cosmology and the origin of the universe, taking our minds all the way back to the very beginning of time. Rest well, holding the warmth of the stars in your mind, and we will complete our journey when you are ready. Lesson 18: Cosmology and the Origin of the Universe. Welcome to our final lesson together. Take a long, slow breath in, and as you exhale, let go of any remaining tension. Let your shoulders completely drop, unclench your jaw, and allow the quiet weight of the night to settle softly around you. Over the course of our journey, we have explored the intricate, beautiful rules that govern our physical world. We have watched the invisible forces of motion pull and push. We have felt the warm, radiating waves of thermodynamics, and we have peered into the microscopic architecture of the atom. We have stood on the heavy, shifting crust of the Earth, breathed in its swirling atmosphere, and traveled outward to witness the brilliant, explosive life cycles of the stars. Now, we have reached the end of our foundational path, and it is time to take one final magnificent step back. In this lesson, we will explore cosmology, the study of the universe as a grand, singular entity. We are going to look closely at its vast structure, its ancient history, and the profound, unimaginably beautiful moment of its beginning. We will trace the story of everything that is, was, and ever will be. Rest deeply now and allow your mind to open to the very limits of time and space as we uncover the origin of the cosmos. To understand cosmology, we must first define what we mean when we say the universe. The universe is not just the collection of stars and planets we can see. It is absolutely everything that exists. It is all the matter, all the radiant energy, all the vast stretches of empty space, and even the relentless forward march of time itself. For most of human history, as we looked up at the night sky, we assumed that this grand universe was static, eternal, and perfectly still. But in the 1920s, a quiet, meticulous astronomer named Edwin Hubble made a discovery that shattered this assumption and changed human thought forever. Hubble was spending his long, freezing nights staring through a massive telescope on a mountaintop in California. He was observing distant, faint smudges of light that were, at the time, thought to be just clouds of gas within our own galaxy. Hubble discovered that these smudges were actually entirely separate galaxies, island universes filled with billions of their own stars, sitting millions of light-years away from our own Milky Way. But his true paradigm-shifting discovery came when he analyzed the light from these distant galaxies. By examining the subtle color of their light, Hubble realized something astonishing. The galaxies were not sitting perfectly still in the dark. They were moving. In fact, almost every single galaxy he observed was moving away from us. And the further away a galaxy was, the faster it was receding into the distance. Hubble had discovered that the universe is not static. The universe is expanding. To visualize this, it is very important to gently correct a common misconception. When we think of things moving away from each other, we usually picture objects flying through the air, like shrapnel from an explosion traveling through an empty room. But this is not how the universe works. The galaxies themselves are not flying through pre-existing space. Rather, the empty space between the galaxies is physically stretching. Imagine you are baking a loaf of sweet raisin bread. You mix the dough, fold in the dark, heavy raisins, and you place the small, dense ball of dough into a warm oven. As the yeast does its work, the dough begins to rise and expand in every direction. If you were to pick one specific raisin and watch it, you would see that every other raisin in the loaf is moving away from it. The raisins are not actively swimming through the dough. The dough itself, the space between them, is simply growing larger. In our universe, the galaxies are the quiet raisins, and the empty space is the rising dough. Everywhere we look, the fabric of reality is stretching out, carrying the ancient galaxies further and further apart in a silent cosmic expansion. This brilliant realization that the universe is expanding today leads us to a very simple, profoundly logical conclusion. If the fabric of space is stretching and growing larger as time moves forward, then it must mean that in the past, the universe was much smaller. The galaxies must have been closer together. If we take this logic and wind the clock backward, reversing the expansion year by year, century by century, we watch the universe shrink. We wind it back millions of years, and then billions of years. The galaxies are pulled intimately close. The temperature rises. We keep winding the clock backward until we reach a point, approximately 13.8 billion years ago, where all the matter, all the energy, and all the space in the entire universe was compressed into a single, infinitely small, and unimaginably hot point. This point is known in physics as a singularity. And then time began. The sudden, magnificent expansion of space from this infinitely dense point is what we call the Big Bang. Again, it is crucial to understand that the Big Bang was not a bomb exploding inside a dark, empty room. There was no room, there was no outside for it to explode into. The Big Bang was the sudden, violent expansion of the room itself. It was the birth of space and the beginning of time. In the very first fractions of a second after this expansion began, the universe was a chaotic, searingly hot soup of pure energy. It was far too hot for even the simplest atoms to exist. But as the universe rapidly stretched outward, it began to cool, much like a hot breath of air cools as it expands from your lips. As the universe cooled, the energy began to settle. Protons and neutrons formed, quietly clicking into existence. About 380,000 years after the initial expansion, the universe finally cooled just enough to allow those wandering, weightless electrons to bind to the protons. In that beautiful, quiet epoch, the very first atoms of hydrogen and helium were born. When these first atoms formed, they locked up the wandering electrons, which finally allowed light to travel freely through space without bumping into the dense, chaotic soup. For the very first time, the universe became transparent. A brilliant flash of light flooded the expanding cosmos. That very first, ancient light is still traveling through the universe today. It has been stretched by billions of years of expansion, cooling down into a faint, invisible microwave hum. We call it the cosmic microwave background radiation, and when our radio telescopes listen to the deep, empty sky, they can still hear it. It is the gentle, fading echo of creation itself. From that first hydrogen gas, gravity patiently went to work, pulling the clouds together to ignite the first stars, which forged the heavy elements, which eventually built the planets, the oceans, and eventually us. This grand, sweeping history of cosmology brings our entire journey beautifully full circle. The physics of motion, the transferring of heat, the elegant bonds of chemistry, the swirling atmospheres, and the life cycle of the stars. All of these magnificent rules we have studied are simply the universe slowly unfolding and organizing itself over 14 billion years. You are not separate from this grand story. The iron in your blood, the calcium in your bones, and the carbon in your cells were forged in the hearts of ancient stars, which were built from the hydrogen born in the very first moments of time. We are, in the truest scientific sense, a way for the cosmos to know itself. The universe expanded, cooled, and organized itself so perfectly that it eventually opened its eyes, looked up at the night sky, and was able to understand its own magnificent origins through minds like yours. And so, we have reached the peaceful end of our foundational journey through physical science. From the quiet logic of the scientific method to the vast, echoing expansion of the cosmos, you now hold the blueprint of how physical reality is woven together. There is nothing left to study tonight, and nothing left to memorize. Let these profound, comforting truths settle deeply into your mind. The universe is ancient, it is balanced, and it holds you safely in its intricate web of physical laws. Rest well now, sleep peacefully, and know that you are a beautiful, deeply connected part of this magnificent continuing story. Good night.